Despite a lot of efforts Microsoft and third parties have made in increasing the reliability of Windows, crashes are still a fact of everyday life in managing a Windows network. A lot of Windows administrators don't realize that, first of all, that crashes can be analyzed to find out a root cause. And even those that recognize that they are able to analyze crashes likely feel that it's too difficult to open a crash dump and figure out what's going on to figure out the root cause. It turns out that basic crash dump analysis is actually relatively straightforward, relatively painless, and just takes a few minutes. Now, some of the techniques we're going to teach you in this section or in this presentation are going to make you crash dump analysis pros. Not experts, but pros. You're going to even be better than the many systems administrators that realize that they're able to analyze crashes with some of the tips and techniques that we give you to turn unanalyzable crashes into ones that you can analyze. I do want to do a level set, though. Turning into a crash dump analysis expert would require a serious investment on your part in learning processor architecture, Windows internals, and just doing a lot of practice of analyzing crashes and looking at the internals of Windows as it's running. The critical problem resolution engineers at Microsoft that analyze crashes on a daily basis are able to look at blocks of memory in the kernel debugger and, without any other hints, recognize data structures sitting there, such as pool headers and IO request packets, device driver data structures, process data structures, and so on. And with that kind of experience and knowledge behind them are able to analyze crashes that most of us would never be able to analyze in real life.
In fact, I remember, Mark, I was teaching our 5-day Windows internals hands-on class with labs to a group of 35 Microsoft support engineers in Europe, and there were several from that critical problem resolution team in the class. We did a lab where we generate a crash that is basically considered unsolvable, something we're going to perform later in the presentation, a buffer overflow where a device driver scribbles over memory, causing it to be corrupted, and the system crashes later in a basically undiagnosable fashion. Well, this engineer in the class who was on this CPR team was able to look at the crash dump and notice patterns in kernel memory and able to solve back to the root cause of the buffer overflow. That's one engineer out of thousands that have taken this class that have been able to go to that depth of analysis.
And that's pretty impressive that they can do that. Now, most Windows systems administrators, when they run into crashes on systems that are occurring, one of the common techniques is to reinstall Windows, unfortunately. So with the information you learn here, you're going to learn that simply just rebooting or falling back on reinstalling is something that you can avoid.
Now, first question is, why does Windows crash in the first place? So why does it paint the blue screen? Windows crashes when it detects that it is sick. Something's wrong in kernel mode, inside operating system data structures, and the system determines that it's too sick to continue, that it would be dangerous to allow the system to continue execution. Examples of things that could trigger a blue screen or a system crash would be unhandled exceptions in kernel mode, operating system or device drivers detecting that a data structure is in an inconsistent state, references to invalid virtual addresses, or even hardware errors. In these cases, the device driver that recognizes the problem or the operating system calls a function in the kernel to stop execution immediately with the goal of preventing data corruption. So really, when Windows crashes, you should thank the operating system because it's looking out for your best interest. Were it to allow itself to continue execution, you'd be running the risk of writing perhaps corrupted data to your hard drive. So this puts a little different perspective on blue screens. When my systems crash, I say, thank you, Windows. I appreciate you looking out for my best interests.
So Microsoft collects crash dumps from customer machines using a mechanism we'll see later called online crash analysis. And they've looked at the crashes that have been submitted and tried to figure out the root causes in order to get a breakdown of what's ultimately causing Windows period to crash. What they found is that roughly 70% of the crashes that get submitted are caused by bugs in third-party drivers. So the majority of the problem isn't really in Windows itself. It's related to the drivers that people are writing and shipping with hardware. About 15% of the crashes Microsoft's unable to determine the cause for because the memory in the crash dumps are too corrupt. Roughly 10% are caused by hardware issues, and this include issues like corrupted or like memory that has single bit errors in it, disks that are becoming corrupt, and roughly 5% Microsoft recognizes is actually being caused by their own code. And that number hopefully is going down over time as Microsoft makes improvements in the reliability of Windows and the drivers that ship with Windows.
One of the things that is a good and a bad thing about Windows is the number of device drivers. There are an incredible number of third-party device drivers. That's great because you can find device support for virtually any hardware device you might want to connect to a Windows system. The number of device drivers Microsoft is able to get some idea on by looking at the crash dumps that come in over the internet that are submitted for online analysis, as well as their own Windows Hardware Quality Lab statistics. As of the spring of 2005, there were 55,000 recognized unique device drivers with an increase of a rate of about 24 new drivers discovered a day. If you take different versions of those 55,000 drivers, there are a total of 220,000 different versions of different device drivers that have been seen on Windows systems that have crashed and had their dumps submitted to Microsoft, with about close to 100 drivers revised a day. So a tremendous breadth of device drivers and different versions running around out there. There's also a huge array of device support, over 1 million unique plug-and-play IDs, unique devices that hardware vendors have built that are supported on Windows systems, with 1,600 added every day. So again, that's a two-edged sword. Great device support in Windows. Unfortunately, some third-party drivers are not up to the quality bar that Microsoft has set. So what we're going to do in the remainder of this presentation is, as Mark said, take you to the level of being a Crash Dump Analysis Pro. We're going to look at the different types of crash dumps that you can configure Windows to take, the mechanism, what happens when a crash occurs, how it writes the dump to disk, some basic internals concepts you'll need to know to perform professional level analysis. Then we're going to look at analyzing what we consider to be an easy crash. Then we'll look at some harder crashes, ones that are really unanalyzable without using some tools to help you to turn them into easily analyzable crashes. In fact, we'll be revealing our crash transformation recipe, what the steps that you should take to take blue screens that are not easily solvable and then hopefully generate ones that are easily solvable. We'll also cover the cases where you're going to have to get down and do some manual analysis in the crash dump. We're going to give you some tips, some basic commands that you'll be able to put on a dump that doesn't have an obvious signature and try to get some pattern, some information that will lead to the root cause. And then finally we'll address the case where Windows is crashing or rebooting spontaneously and there's no crash dump to be had. What can you do in the case of systems that crash without leaving a dump? And also the case where the system is hung in a state where you have no keyboard control and no response from the mouse. Windows provides several options to configure the system to record its state when the system crashes. Let's take a look at these options by going to the Start menu, right-clicking on My Computer, choosing Properties, going to the Advanced tab, choosing Startup and Recovery Settings. And here we have some of the configuration options for what Windows should do when it crashes. If you look at the center section on a system failure, the default is to write an event to the event log, send an alert, and automatically reboot. Let me make a comment about the default to automatically restart. Back in Windows NT 4 and earlier, the default was not to reboot after a crash. So when Windows took a blue screen, the user saw it on the screen and they had to do a hard power off, power on to reboot the computer. Control-Alt-Delete doesn't work at that point. So people were more aware of a blue screen. Today, since Windows 2000, the default on Windows 2000 systems and later is to automatically reboot after a crash. And because the default crash dump type since Windows 2000 has been to record minimal information, the saving of the crash dump is so fast that when the system blue screens, there's basically just a flash and the system reboots. And it's so fast that people don't see the blue screen anymore. In fact, I worked with a customer that had hundreds of blue screens across their enterprise, across about 3,000 desktops for about a period of a week before somebody finally reported the problem. And the reason was the users were working and all of a sudden they had to log in again. And they figured, oh well, my system restarted, I'll log in again and go back to work. So people are seeing blue screens much less today because of that default. If you look down at the next section where it says write debugging information, there are three choices. No debugging information, small memory dump, kernel memory dump, and complete memory dump. Let's talk about complete memory dump first. Prior to Windows 2000, your only choices were no dump or a complete dump. A complete memory dump causes Windows to save the contents of all of RAM for analysis after the crash. And the problem with this option with systems that had large amounts of memory was the amount of disk storage required to save the dump. If you look at high-end 64-bit servers today, RAM maximums are already in the terabyte range and are only going to be increasing. So in Windows 2000, a new compromised dump type was added called the kernel memory dump. Kernel memory dumps record only the operating system related memory in the crash dump. And if you think about it, if the operating system is crashing, it's because something is wrong inside kernel memory. Some data structures that are manipulated by the operating system or device drivers are in an inconsistent state. So it's overkill to save all of RAM. Instead, saving just the kernel memory means that the dump will have the information that is necessary that could be used to analyze the cause of the crash. How big is a kernel memory dump? Really, it depends. It depends on how many processes are active, how many IOs are in process, how many drivers are loaded, how many sessions. So there's no magic number that you can tell upfront based on the size of the system's RAM. In the range of 10 to 20 to 30% of RAM at the high end is probably a rough range of the size of a kernel memory dump. The last crash dump type is called the small dump or mini dump. And this was added in Windows 2000 as a way for Windows by default on client machines to record just the minimal amount of information needed for the crash.
A mini dump, because it's so small, it's 128 kilobytes on a 64-bit Windows system, which is what we're running here, and 64 kilobytes on a 32-bit Windows system, contains just a tiny amount of information that includes what's called the bug check code and associated parameters. We're going to talk about what those mean in shortly. It also contains the list of drivers that were loaded at the time of the crash, information about the process that was currently executing at the time of the crash and its thread, a few other pieces of data that the crash function thinks might be relevant or useful for a crash dump analysis. Really not a whole lot of information you can store in there. The advantage of mini dump, besides its small size, is that Windows keeps a record of each of them as they occur, and when you go configure the mini dump, what you see is that you don't need to specify a particular file, you specify a mini dump directory down here. And the default is to place the mini dump directory in the system root. Let's go take a look at the mini dump directory on this system. And you can see that I've got a few mini dumps in here. And the naming convention is clear if you look at them. Mini, month, date, year, and then a dash and an index number, so that if there are multiple crashes on the same day, each one will have a unique name with a unique index number.
By the way, Mark, I've found that very few people are aware that they've even had crashes. As we mentioned, by default, Windows 2000 Professional and XP Professional is configured to automatically reboot after a crash. Writing the mini dump is so quick that there's seldom a visual cue that the system crashed. So it might be an interesting check to look on your own system, go to your Windows mini dump folder, see if you've got some mini dumps, and if you have some, with the information we're going to explain later, go try to analyze those dumps.
Now, a lot of people say, well, mini dumps are so small that it's really not enough information to do an effective crash dump analysis. And that's true. It can limit the effectiveness of crash dump analysis. But the fact is, even if you configure your system for kernel dump or memory full dump, you get the benefits of mini dump and the larger dump size that you've configured, because Windows XP and later is automatically configured to generate a mini dump out of the larger dump size at the time of the boot. In addition, if somebody gives you a kernel dump or a full memory dump, the kernel debugger itself is able to extract out of those crash dump files a smaller version mini dump. So you're really not losing anything by going with a larger dump file. You get the advantages of the larger dump file for help in crash dump analysis, and the smaller one, which you can even email to somebody as an attachment. They're that small.
Now, Mark, what we generally recommend is that you configure your systems for kernel dumps. We think that's the best compromise. The default, again, on Windows XP is the mini dump. While that's okay for the most straightforward crashes, crashes that are more difficult to analyze require more than the limited information recorded in the mini dump. So you could choose as a default on your enterprise the kernel dump, and like Mark said, if you have a kernel dump which is of a large size you need to send off for analysis, you could extract a mini dump, send it off as a short email attachment, and then offer the kernel dump if necessary.
In fact, Windows Vista is by default configured to generate kernel memory dumps, so Microsoft's recognized the value of having a kernel memory dump available if necessary.
Now, when Windows detects an internal consistency, a call is made to an internal function called KEBugCheckEX. This is a function in the operating system, documented in the device driver kit, available to device drivers to call if they find a consistency issue, some data structure that has contents that or a condition that should never occur. So Windows itself, as well as device drivers, are encouraged to make calls to this function if they detect an internal consistency failure. This function takes 5 arguments. It takes first an indicator as for the main reason for the crash, called the stop code or bug check code. Each of these stop or bug check codes takes optionally up to 4 parameters that give extended information for the reason for the crash.
There are about 150 defined stop codes, and device driver developers include a header file that's part of the device driver development kit that includes the definitions for the stop codes. So if a device driver programmer wanted to call KBugCheckEX, they could refer to one of the predefined stop codes. It's generally, though, considered bad practice to crash in a driver. A driver should handle errors generally gracefully. The kernel, though, has a choice of those 150 stop codes for the kind of giving you a clue as to the general category of the crash when it happens. And the debugger tools reference part of the debugging tools for Windows package that you can download from Microsoft's website. So let's go take a look at where we get the debugging tools for Windows package here. Finding it on Microsoft's website it really as easy as typing in debugging tools and doing a search and going to the first found reference. This is the debugging tools for Windows homepage where you can download either the 32-bit or the 64-bit versions of the debugging tools. Once you've downloaded and installed the debugging tools, they place themselves on your start menu. I'm going to go to the debugging tools for Windows 32-bit package and open the debugging help file and open it up and go to debugging techniques, bug checks, bug check code reference, and you can see here that there's entries for those 150 or so stop codes with information that help you troubleshoot a crash of these particular stop codes. So let's pick one right here, like IRQL not greater or equal, and see what kind of useful advice the debugging tools help provides us. So let me zoom in here and let's see what it says. The IRQL not greater or equal bug check has a value of 9. This bug check appears very infrequently. So you can see that this is just a tremendous resource of useful tips and information on
Really
troubleshooting crashes.
Yeah, that's a good addition they made there.
Actually, I'm not being fair. For the real common stop codes, like IRQL not less or equal, there is a good deal of helpful information, including a description of the parameters. As we'll see, though, the process of analysis makes this information readily available to you. So I rarely have to turn to the debugging tools for help file to find out this information. It's presented in other ways, though there are sections in here that have general troubleshooting techniques and other information to help you troubleshoot crashes.
Also, Mark, that Microsoft Knowledge Base, which you can get at microsoft.com/support, is another resource for searching for articles on specific bug check codes. So if there's some difficult to solve crash, taking a look in the knowledge base is typically worthwhile because there might be a support article that covers a generic crash code type but has some specific text related to a particular device or condition that you might be experiencing. Mm-hmm. Now, when the operating system or a driver calls the function in the kernel to crash the system, what happens? What does the operating system do at that point? First, it turns off interrupts because the operating system doesn't want to invoke any other device drivers to handle further I/O operations. It wants to stop execution as fast as it can. If it's a multiprocessor system, it sends out an interprocessor interrupt telling the other processors to stop dead in their tracks, and they literally perform a halt instruction. Whatever they're doing in the middle of processing an interrupt, in the middle of running some user thread, in the middle of some operating system function, they halt, dead stop. The processor that is invoking the crash then proceeds to paint the blue screen. So there's now a visual indication that the system has crashed. The information on the blue screen may or may not be enough to solve the crash. It may point to the driver at fault. It may not. But again, since most Windows systems are configured to auto reboot, that's going to stay on the screen for such a short period that nobody's able to read it. So it's at this point that Windows then checks to see, was it configured to write a crash dump, to record the state of the system at the time of the crash? And by default, Windows is recorded to do that, either mini dump for client systems or full dumps for servers. As Mark mentioned, in Windows Vista now the client systems are configured to take a kernel dump. What's interesting though is when Windows crashes, if it has been configured to write the crash dump, it records the information not in a new file on the disk, but rather in the paging file. So that's one important point about taking crash dumps. You must have a paging file on the boot volume, on the volume that the Windows directory that you're running off of lives. That paging file obviously has to be big enough to record the crash dump, whether it be a full dump, a kernel dump, or a mini dump. The reason Windows writes the crash dump to the open paging file is that it's basically too dangerous to create a new file on the disk, because that would cause invoking large portions of the I/O system and the file system driver. And we'll see shortly what Windows does to verify that it is even safe to take that step, because it's possible that device drivers or perhaps the operating system has corrupted the information that it's about to use to even save the information in the paging file.
So it turns out when Windows boots and it determines that you've configured a crash dump, it gets a mapping of where the paging file is on disk sector by sector, which is one of the reasons why the paging file has to be on the boot volume. It's one of the only volumes on a Windows system that has to be mapped directly to a contiguous list of sectors on disk, so that the crash dump code can realize that a particular sector in the crash dump file, an offset in the crash dump file, maps to a particular sector on a disk without having to do volume management kind of semantics that you'd have to do if it was on a RAID or striped volume. The paging file map is obtained, and relevant components that are involved with generating a crash dump are checksummed, including the map, including the code of the boot disk mini port driver, and including the crash I/O functions that are involved with writing the dump. Now, the boot disk mini port driver is the driver that is normally used by Windows to access the disk that the Windows directory is on. But it includes special functions that don't rely on any other services of the Windows I/O system, or just very few, that write directly to the disk using what's called programmed I/O. So it doesn't use the normal disk high-speed DMA, for example, because it's just not safe to rely on much of the system at this point. The checksum is saved away, and at the time that Windows crashes, Windows goes and re-verifies the checksum, makes sure that all of the components involved with writing the dump haven't been corrupted by whatever's caused the problem. And if at that point there's no problem, the checksums match, it will initiate the writing of the crash dump to the paging file on disk.
So therefore we can see that there are cases that Windows is going to crash and there will be no record of the crash. We're going to explain later how to deal with systems that crash but don't record their state. It's actually pretty straightforward to gain control and be able to look at the state of the system at the time of the crash. But what are some of the reasons, most common reasons, that you may not have a crash dump after a crash? Well, the first one is interesting. Because the crash dump is recorded in the paging file, if the system crashes before the paging file has been opened, there is no way to save the dump. And we're going to see in our discussion later that this is a step that happens relatively well into the boot process. The paging file is opened by the first user mode process, the session manager, smss.exe. So there's a lot of device driver activity that happens before that step. The boot start drivers are loaded and initialized. System start drivers are loaded and initialized. So any crash during the early part of the operating system initialization, you'll never have a crash dump because the page file has not been opened. Again, we'll see later how to gain control at the time of a crash at this early part of the boot so that you can then analyze the reason for the crash. Another reason could be spontaneous reboots. And I know I was dealing with a server that was in the middle of the night having a spontaneous reboot due to a hardware problem, actually, that caused the system to reset without entering the crash dump code. Other examples would be a hung system. If the system is in a hard hang or unresponsive, then there's not going to be a crash dump available because it's not crashed, it's just in a dead or hung state. Less likely is that the paging file is too small, because when you configure the system for crash dumps, if the page file on the boot volume is too small, the control panel applet will complain at you. But if you ignore the warning, you could have a system configured to take a full memory dump with a page file that's too small to hold it. And then the last reason could be on the reboot, when the dump is extracted, if there's not enough free space in the Windows directory, then the dump is lost.
And the paging file too small problem can be an issue if you've configured your system to generate kernel dumps and have taken advantage of that fact to size your paging file smaller than the amount of physical memory. For example, if you've got a multi-gigabyte server, you're going to probably want to take advantage of the fact that you can generate a kernel memory dump and not have to create a paging file as large as the physical memory on the system, because generally the size of the paging file is inversely proportional to how much physical memory you've got on the machine. But then you run the risk of the kernel memory dump not fitting in the paging file that you've specified. So what we recommend in such situations is to first create the system with a larger paging file and generate test crashes with a tool that you'll see later called Not My Fault. You can do this pretty easily. Figure out how much kernel memory you'll typically see in a crash dump under kind of production, everyday system activity, and then size your paging file down to get closer to that level. So let's take a look at what happens at the time of the reboot now after the system's crashed. As Dave mentioned, the first user mode process to start up is the session manager, smss.exe, which initializes paging by calling a kernel mode function ntcreate paging file. The ntcreate paging file function looks in the paging file and sees if there's a crash dump header in there, and if it is, it marks that part of the paging file as off limits. A little bit later in the boot process, the winlogon process starts up. Winlogon is responsible for interactive user logons. Winlogon looks in the paging file by calling the system and asking if there's a crash dump in it, and if so, launches a small program called SaveDump, which its sole purpose in life is to open up the paging file, read out the contents of the crash dump, and save it to the target location that you've specified in that crash dump configuration dialog. It also configures the Windows error reporting program to run at the first user logon to the system.
Now, Windows error reporting is a new mechanism that was added in Windows XP. It's also part of Windows Server 2003. Windows error reporting is the mechanism behind the message box that perhaps you've seen when a process crashes, that it says, "We're sorry for the inconvenience, please tell Microsoft about this problem," and the two options to send the error report or not send. Let's take a look at the configuration for Windows error reporting by going to the Start menu, right-clicking on My Computer, choosing Properties, going to the Advanced tab, and pressing on the error reporting button towards the bottom of the property page. And we can see that by default Windows error reporting is enabled for both Windows operating system failures as well as programs. Windows operating system failures relate to blue screens or system crashes. So if Windows error reporting is enabled for the Windows operating system, then WinLogon, as Mark mentioned, will configure the system to, on the first user logon, run the dump prep tool, which will, if the system is configured by default, present a little message that says the system has recovered from a serious error, give you the option to submit the error report to Microsoft. Now, it's interesting that if you're using the group policy editor, you can make some customizations there. For example, you can change the message text. Instead of "please tell Microsoft about the problem," you can say "please tell internal technical support," or "please call," and give some internal extension. You can also configure through group policies to not show the user interface. So in other words, on the reboot after a crash, to automatically submit the crash dump so that the user doesn't have the option to not submit it. And finally, with group policies, you can configure the crash dump location so that instead of sending the crash dump to a Microsoft server to be analyzed, it can be copied to an internal share where your internal tech support staff can then analyze the crash dump. This is built into Windows XP. It does not require any additional software. All it requires is a share that's writable by all users on some file server in the network. This could be interesting in an environment where you're not connected to the internet at all, but you still want to be able to record crash dumps on your Windows machines, or in an environment where you'd like to do some of your own analysis before sending crash dumps off to Microsoft. For example, there could be some sensitive information in the crash dumps, names of drivers that are loaded, potentially some text of buffers, system buffers that have contents of files on the disk that are sensitive. So perhaps you want to be able to look at those dumps internally, and for the ones that you can't solve, selectively send them to Microsoft. So dump prep, when it runs, if configured, generates a small XML file that has a description of the system, the version number, the list of loaded drivers and their version number. It then, if you select the option and it's configured to do so, submits that dump for analysis. It submits the XML file and a mini dump. The XML file, which has the list of drivers, is one of the pieces of information Microsoft has used to collect that database of known drivers across all Windows systems that has led to some of the statistics we mentioned earlier.
Online crash analysis was introduced with Windows XP, and a lot of you have probably seen online crash analysis appear through that Windows error reporting dialog that pops up after you reboot the machine after a crash that says, "Windows has encountered a serious error. Please send this report into Microsoft." If you've done it, you've been taken to the online crash analysis website. And we speculated at one point, Dave, that the kernel developers that were involved in the security push at Microsoft a few years ago, if they had security problems in their kernel mode code, they're sent to a warehouse. and are sitting there. There's no heating, no air conditioning, and they're forced to analyze crashes that people submit to the online crash analysis website.
And I also heard that those developers that had 2 or more bugs that they were found to introduce into code, they have to analyze the crashes with Notepad.
So for those people that are watching that maybe work at Microsoft and wonder where your office mate or the guy down the hall disappeared to for a few months, they're probably there. Actually, that's not really what's happening. The online crash analysis website is an automated server with a database backend. And what it does is it implements the same kind of crash analysis that we're going to show you how to do yourselves. And it generates what's called a signature, a bucket ID for the crash, kind of a unique thumbprint. And then it uses that thumbprint to look in the database to see if one of the online crash analysis engineers that analyzes crashes as they come into Microsoft has determined the root cause of the crash. If so, the database will return information to the OCA website about what page you can go to download a fix, what knowledge base article describes the problem, take you to a vendor site where you can get an updated version of the driver.
And this has actually worked for you and I. Both Mark and I have each had crashes that we've submitted to Microsoft, and there was a solution. On the spot, we got pointed to a knowledge base article that had a pointer to an updated driver. So the system really does work.
And I don't want to pick on the vendor that you're seeing here on the online crash analysis website, but this driver that you see appear in the website, shortly after their initial release of Windows XP, started causing my machine to crash when I'd go to a certain page in a help authoring tool with a loaded help file. Every time I go to that page, instantly I'd get this crash. And back then, right after the release of Windows XP, Windows error reporting had just been introduced, and there were some questions out there about what Microsoft was doing with the information, whether they were doing inventories of people's systems. So I was reluctant at first to send this in to OCA. Eventually, I got over my reluctance. I'd decided that Microsoft probably was not kind of doing anything nefarious with the information that was going up, and I submitted it. And lo and behold, I got taken to this page right here, which told me that there was a fix for the problem that I was encountering. I went to the update site, downloaded the new driver, and the problem completely went away. Now I'm wondering if that was actually a setup by Microsoft, if maybe they had their vendors put buggy drivers with their initial release of Windows XP just to get people excited about Windows online crash analysis.
I don't think so, Mark.
Well, that was the first and last time that OCA has ever helped me, unfortunately. See, most of the time, no, but Microsoft, OCA is a very valuable tool, and it does a lot of analysis.
And you recommend people
and
submit
I absolutely recommend people submit it, because not only when you submit it could you get a resolution, but you're also giving Microsoft an idea of how prevalent this particular type of crash is, and they're obviously going to spend time going to analyze the crashes that customers are experiencing frequently. But more often than not, what you might see, and what I've seen, is an OCA page that looks like this, which tells you an error is caused by a device driver. And this simply means that the analysis engine was not able to find an entry in that database for that particular bucket ID.
But at least, if you notice, Mark, Microsoft thanks you for submitting the problem report.
And I'm glad that they're happy, and I know that I'm helping them figure out the cause of the problem and maybe help me in the future or help other people that encounter the problem.
But if you read the second sentence, that's not really true, is it? It says Microsoft is unable to specifically determine what caused the problem you reported.
Well, that's right. In fact, what's going on underneath the hood there is that the online crash analysis has done the same analysis we're going to show you how to do. Behind the scenes, the analysis is more often than not determined that a particular driver on the system is probably the cause of the crash. It's just that it can't tell you about its suspicions, because if it were to do so and say, hey, we think this guy caused the crash, the first thing that's going to happen, within minutes probably, is Microsoft's going to get a phone call from a certain company's lawyers claiming that they're being smeared on the OCA website. So they're not able to tell you about their suspicions until a human actually sits down, analyzes the crash, and actually is certain that that driver is the cause of the problem.
So the analysis is correct. They know. It says a device driver installed on your system caused the problem. It's just they can't tell you which one.
Right.
We're going to be showing you how to open such a crash dump, and you'll be able to see the device driver that they think is causing the problem. It's just they can't tell you that driver name automatically.
Right. So let's move on, and next we'll talk about analyzing a crash yourself. Before you can analyze a crash, you actually need to do some preparatory work. You need to get the tools that are necessary for looking at the crash dump. Microsoft provides these tools in the form of the Debugging Tools for Windows package, which is a free download from their website. Let's go to the Debugging Tools for Windows website, where we can see the Debugging Tools for Windows homepage here. So this homepage provides links to download the 32-bit debugging tools for Windows as well as the 64-bit debugging tools for Windows, and provides information about getting started in crash dump analysis.
Just to clarify that, Mark, if you're needing to analyze a 64-bit crash dump, can you do that on a 32-bit system?
You can. You can do crash dump analysis on either platform of either type of target crash.
So the debugging tools that you choose depends on what you're installing on, not the type of crash dump you're analyzing.
Good point. There's two tools that come with the Debugging Tools for Windows package, and one is WinDebug. It's a graphical user interface tool, standard Windows application, and the other one is KD, which is a command line tool. They have the exact same functionality. Which one you use to do crash dump analysis is really a matter of personal preference. I know that kernel engineers at Microsoft, they feel like they're cooler by using the command line version, but I personally prefer using WinDebug because you can open up multiple windows concurrently and look at data, different types of data in those different windows.
But they provide the same functionality, so you're not losing anything by going with the GUI version. In effect, when you open a crash dump with the GUI version, you're in a command line window using the same command line commands you would use in the command line version of the debugger.
And in a minute, we're going to show you that analyzing a dump is as easy as opening the crash dump file in using one of those two debugging tools.
So I find the hard part sometimes is clicking on the file open.
Right, and we're going to walk through that step carefully here in a second.
But that's as hard as it is. Clicking on file, open crash dump, open it and click OK. Now, in order for the debugger to perform its basic analysis, it does require access to some special files that Microsoft provides called symbol files. These symbol files are generated when Microsoft builds or compiles and links the Windows operating system binaries. They don't ship with Windows. They're available for separate download, or as we're going to see, they're accessible automatically from a server at Microsoft that you can configure the debugging tools to automatically download the required symbol files from. The debugger needs at least the symbols for the kernel image. It needs the kernel symbol file to analyze a crash dump. And the kernel image is ntosskernel.exe. That's an image in the Windows System 32 folder. And by the way, even on 64-bit Windows, the 64-bit kernel is in the Windows System 32 folder. So at a minimum, you need the symbol file for ntosskernel.exe. Symbol files these days have the extension .pdb, so the file of interest is ntosskernel.pdb. For full analysis of a mini dump, the debugger also needs access to the kernel image itself, the actual executable. It will analyze the dump without having the exe, but if it has the exe, it can perform some additional analysis steps. So two things are needed to perform a reasonable analysis on a Windows crash dump: the symbol files for the kernel image, and if it's a mini dump, the kernel image itself.
So it sounds like a big pain having to go get these symbol files and figure out which version of the kernel you've got and find the images for them, and especially if you've got a network with lots of different versions of Windows. Microsoft has made obtaining the symbols incredibly easy because they've posted all of the symbols to all released versions of Windows up on what they call the symbol server. It's a specific server on Microsoft's website, and you can configure the debugging tools to go to that symbol server looking for symbols whenever it needs them. So in other words, on demand. When you open a crash dump for a version of Windows that you haven't previously opened, the debugging tools will realize that it needs the symbols for the kernel, go up to the symbol server, and download them to your local symbol cache that you specify. To configure your debugger to use the symbol server, you go open up the debugger. So I'm going to open up WinDebug here, Debugging Tools for Windows. Go to the File menu, go to the Symbol File Path menu entry, and then type in the magical string that configures the symbol server, which begins with the letters SRV asterisk. Following the asterisk, you specify the top-level directory of the local symbol cache, in my case, C:/symbols, followed by another asterisk, and then the URL of the Microsoft symbol server, http://msdl:/microsoft.com, download symbols. This is documented both in the Debugger Tools help file as well as on the Debugging Tools homepage at Microsoft.com. And that's as simple as it is. The debugging tools will now go and fetch the symbol files. Let's go take a look at my local symbol cache. And you can see that I've got symbol files for many different components of Windows, everything from the class PNP driver to NTOS kernel, NTDLL, NT-kernel MP, the kernel, different versions of the kernel here in these files. And if we go into one of these, you'll see that the subdirectories are labeled with a hash of the kernel file, so that if Microsoft releases a new version of NT-kernel-mp.exe, multiple versions of the symbol files for that file image can reside in this directory, each under a separate subdirectory with a unique hash name.
So for example, as you open various versions, various dumps from different kernel versions, the symbol engine is going to download more and more versions of the kernel symbols. You don't have to worry about this directory tree. This is all managed by the symbol server, the client code in the debugger. So it's interesting to look here, but it's going to do the work of putting the symbol files in the right version-specific directories.
So in networked and corporate environments where you don't want the machines that are doing crash dump analysis to necessarily go to Microsoft Symbol Server on demand in that way, where it might be not even publicly accessible to the internet, you can use a tool that comes with the debugging tools for Windows package called SymCheck to force the symbol downloads. And SymCheck is as easy to use as finding it in the debugging tools for Windows package, typing SymCheck, and I'm scrolled off here. SymCheck. And you see when you enter it, it has a list of options. Really all it takes is you to point SymCheck at a particular directory like C Windows, System32, star.exe or star.dll, and this will automatically, assuming you've got the symbol path set as an environment, pull down the symbols from the symbol server. And how do you set the symbol file path as an environment variable? It's nt symbol path equals, and then you would enter the same string that we just showed you.
So Mark, for example, that client that I said I work with that has that network disconnected from the internet, they have somebody in their IT staff that periodically takes the current Windows directory for their standard XP client installation and their server Windows directory to a machine on the internet. They do a SymCheck on the whole Windows directory, all the files, the exes, the DLLs, and the drivers, generating a pull down of all the symbols that match those versions. Then they take that symbols tree, that huge directory of PDB files that was generated by referencing the symbol server, back into the internal corporate network. They have a share set up, so the tech support staff internally, they point their Windows debugger to the internal share using the syntax srv star // name of server / share name, so that everybody shares that common set of symbols that have been downloaded from the internet.
And I just want to point out one thing about SymCheck. You don't have to set the environment variable to point at the symbol server. SymCheck takes the /s switch, which also is where you're able to specify the symbol server path for SymCheck to reference as it downloads the symbols.
Now, before we get into analyzing crash dumps, it's important to review just some basic internal concepts, some mechanisms, some terms in the operating system that you're going to see referenced in the debugger and some of the explanations for the crashes, and also some of the debugger commands that we're going to suggest that you use to do some manual analysis. So let's just review 5 key internals concepts: processes, threads, the memory protection model, interrupt request levels or IRQLs, and the concept of stacks.
A process is basically a container. It represents an instance of a running program on Windows, and as a container it holds within it a few different things, including an address space. So this is the code and data that's referenced by the code that's running inside of the process is going to be stored in the address space. Handle table, which is a list of open resources kept open by that process, and resources include files, registry keys, synchronization objects. And finally, a security token that is the security context under which this process is running. It would represent the logged on user, for example, and the groups that they belong to at the time they logged on. If we open up Process Explorer to take a look at the process list, these are processes, each representing an instance of a running process. I mentioned security token being one of the aspects of process, and the security tab in the process properties dialog for an individual process would show you the items stored in the token.
Inside each process is at least one thread. On Windows, threads run, processes don't run. So threads are the unit of scheduling. Threads contain the execution state, the register values, the instruction pointer, the stack pointer. So it's not technically correct to say that the Outlook process is running. It would be correct to say one or more threads in the Outlook process is running. So when a process is created, Windows creates an initial thread to begin executing the main entry point for that program. Now that initial thread can create additional threads to perform other work in parallel. All threads in a process share the private address space. So it's up to the programmer to synchronize access to shared data within the address space among these threads. In fact, that's one of the complexities of having multiple threads in a process, is this synchronization. But it's essential if you want an application to scale across multiple processors to divide it into multiple threads. So applications that are multi-threaded, if programmed properly, may be able to perform work in parallel on multiprocessor machines. If we go back to Process Explorer allows you to examine inside a process. I'm going to pick the Explorer process. I'm double-clicking, and I'm going to the Threads tab. And here's an enumeration of the threads inside the Explorer process. This first one that I have selected right now, Explorer.exe module entry, that was the main thread. That main thread then has created additional threads that we can see in the process.
So as part of the architecture, the Windows provides a few different types of memory protection. One, it gets kind of for free because anytime a process is executing, the address space of that process is mapped into the processor's memory management hardware. And that means that one process can't see the address space of another one just by virtue of the fact that it's not present. It's currently not loaded into the memory management hardware. And that doesn't mean that a process can't access the address space of another process, but in order to do so, it has to follow Windows security principles. It has to open the target process and then use special APIs to gain access to the remote process's address space. But another aspect of the memory protection model in Windows is based on the fact that, or deals with the fact that the address space actually consists of both the user's process address space as well as part of the address space that's dedicated towards mapping the kernel, drivers, and the data that they both use. And it would actually be a problem, a reliability and a security problem, if user mode components like Notepad could reach into kernel mode and read the data out of there or even modify it. And so for this reason, Windows relies on help of the memory management hardware to mark pages that represent kernel address space as being system pages. And the memory management hardware on processors Windows run on prevent anything running in user mode from accessing pages that are marked as system pages. To do so would be caught as a violation.
So in order for a thread that makes a system call, which then has to enter operating system code and access kernel memory, a transition has to occur. And threads make call a function in a DLL that performs a special instruction that safely transitions into this elevated processor access mode. On the x86 and the x64 platforms, this elevated processor access mode is called or implemented by using ring 0. So kernel mode code runs in ring 0, user mode code runs in ring 3. So threads are constantly switching from user to kernel mode and back every time they make a system call. And when that switch is made, the thread is now executing in kernel mode, and now the operating system and the drivers have access to that kernel mode protected memory. Another key internals concept that you'll see referenced in names of bug check codes and also in explanatory text out of the kernel debugger is the notion of the interrupt request level, or IRQL. In fact, one of the most common crash codes or bug check codes is the IRQL not less than or equal. And after we explain IRQLs, you'll have a better understanding of what that crash code means. Basically, IRQLs is a software concept. This is not related to hardware IRQs, although there is some connection on single processor systems, that is used by Windows to prioritize its own work. It's basically the priority of what's happening on the processor at that point. On a multiprocessor system, one processor could be at a higher IRQL than another. So software and hardware interrupts map to these software-generated interrupt request levels.
There's a few key URQLs when it comes to Windows running and crashes. One is passive level, which is at the bottom. It's the lowest IRQL, It essentially is the IRQL that means that no interrupts are masked at all. No software interrupts are masked, no hardware interrupts are masked. And by definition, if the system is executing user mode code, the IRQL is passive level. The only time that the IRQL can be elevated up to higher levels is if it's executing kernel mode code in response to software-generated interrupts or hardware-generated interrupts that trigger the execution of interrupt service routines or deferred procedure calls. Even in kernel mode code, though, most of the time Windows tries to remain at passive level simply because it provides better response to devices that are interrupting the system to keep their interrupts unmasked. The next IRQL that's relevant when it comes to crash dump analysis is dispatch level. This is a software interrupt level, and scheduler operations are mapped to this interrupt level. In other words, when the scheduler is executing on the system, it raises the IRQL to dispatch level. And other operations can raise the interrupt request level to dispatch level. When that happens, though, the scheduler is disabled. So one way that a thread running in kernel mode can ensure that it's not preempted by any other thread on that processor is to raise the IRQL up to dispatch level. This turns off the scheduler, and now that thread can run through whatever operation it's performing to completion. When it's done, it drops the IRQL back to passive level and re-enables the scheduler.
Now, a thread itself isn't doing that. That's going to happen inside the operating system.
That's right. It has to be in kernel mode to be able to raise the IRQL up to a level above passive level. One of the side effects of that rule that the scheduler is off at dispatch level is that a driver executing at dispatch level or a level higher than that cannot take a page fault. It cannot reference a piece of memory that's marked as pageable that is not present, because to do so would trigger the memory manager page in handler, which would be forced to issue a disk I/O and then suspend the thread until that disk I/O is complete, until the data that was referenced has been brought in from disk, either a map file or the paging file. And then in that process of pausing the thread, of having it wait for the I/O to complete, it's basically calling out to the scheduler and saying, scheduler, you need to find another thread to run on the CPU. But remember that at dispatch level, the scheduler is off. So this is a violation of Windows internal synchronization architecture, and thus would end up causing an illegal operation or be recognized as a problem on Windows. We'll take a look at that in a little bit, real examples that causes crashes.
Another key resource to analyze crashes on Windows is the stack. The stack represents the data that the hardware records and that the device drivers that are calling operating system functions record that allow nested function invocation. So in other words, when a device driver calls the operating system, it's information that's stored on the stack that is used to pass parameters to the operating system and then to return back to the function that called it. So the stack stores the parameters passed, the return address, and then local variables, information local to the function that's processing the request. Each thread on Windows actually has two stacks, one for the user mode execution of the thread. That stack lives in the user address space and therefore is accessible to any thread in the process. When a thread enters kernel mode, when it invokes a Windows system call, that thread now runs off its kernel mode stack. The kernel mode stack for each thread lives in the kernel address space and is not accessible to the threads that are running in user mode.
So let's take a look at the way that stack frames are built up by taking a look at this picture, which shows the stack frame structure as it exists after function 1 is called function 2 and function 2 is called function 3. The stack frame highlighted there is function 2's stack frame, which consists of the parameters that function 1 passed to it on the stack. You can see that at the top of its stack, parameter 3, parameter 2, parameter 1. And then the return address is saved at the time function 1 makes the call to function 2. That is what the hardware saves, so that when function 2 returns, the hardware knows where it should pick up execution inside of function 1. Function 2, after it's called, the first thing it does is set up what's called its frame pointer. So it saves the frame pointer onto the stack, and then it might have some local buffers that it wants to use temporarily while it's executing. These local buffers it allocates there on the stack, and you can see there are two of them, local variable 1 and local variable 2. Function 2, when it goes to call function 3, passes the arguments to the function on the stack in the same way it was passed arguments. And you can see there right below its frame, the stack frame for function 3, which includes two parameters passed to it by function 2. There's cases, though, where the stack is easy to look at, easy for the debugging tool engine, the analysis engine to parse, and other cases where it's not so easy. The structure that we just examined is one where it's very easy for the analysis engine to figure out what's going on. The stack frame pointers clearly delineate the areas that correspond to each of the functions in that nesting, but other calling conventions pass things a little bit differently, organize things a little bit differently. One of the commonly used calling conventions inside the kernel itself are what are called frame pointer omitted calls, or where there's no frame pointer saved on the stack, and that makes it difficult for the analysis engine to figure out where the frames are unless it has symbols. Now we're going to see that the kernel, the analysis engine has symbols for all of it, the Microsoft code, but if you've got third-party drivers that are on the stack and they're using calling conventions that don't use the frame pointer, it's extremely difficult for the analysis engine to figure out where the stack frames are, and a lot of times it makes guesses, and it'll tell you that it's making a guess as to where the frame pointer, where the frames are located.
Let's look how easy it is to analyze a simple crash, a crash that has an obvious signature that points very clearly to the culprit. When you open a crash dump with the Windows debugging tools, they automatically perform an analysis and give a guess as to the culprit that caused the crash. And they simply display, when you open a crash dump, probably caused by, and then it lists the kernel mode component, the device driver, or sometimes points the finger at the operating system itself. Now, when you open a crash dump, the debugger is internally invoking a command that you can also use yourself explicitly, and that command is bang analyze, exclamation point analyze. That command displays minimal information about the cause of the crash. The stop code, the parameters that were passed to that stop code, and then the guess at the offending driver. How does bang analyze make this determination as to who might be the culprit for the crash? One of the key resources that it looks at is the stack. Sometimes the bug check parameters point to the instruction pointer that is the offending instruction. Using the loaded module list, it can determine in what driver that instruction fits. In other cases, it uses heuristics to walk the stack, determine who was active at the time of the crash, and the debugger actually performs a little bit of racial profiling. If the crash occurs inside the operating system, but the caller of the function in the operating system that triggered the crash was a third-party driver, the debugger will more often than not say probably caused by and point the finger at the third-party driver, even though the crash itself was caused by an operating system function. But it's likely that that operating system function was passed some bogus data, a pointer to a corrupt data structure or some parameter that was invalid. So if the debugger, when you open a crash dump, does say probably caused by NTOS kernel.exe, the operating system itself, or any other component in Windows, like the windowing system driver, win32k.sys, or the file server driver, srv.sys, or any other base device driver that ships with Windows, don't believe it. Your first assumption should be that Microsoft is not at fault. And they have the data to prove it. As we discussed earlier, 70% of the crashes that come into Microsoft are proven to be bugs in third-party drivers. Another 15% is unknown because memory is too corrupted, which probably means that it was a third-party driver. So it's probably safe to say that more than 80% of the crashes are third-party drivers. So if the debugger decides that Windows was the cause for the crash, then you're going to need to do some more digging to get to the root cause.
We're going to use a tool that I developed called Not My Fault to generate some of the crashes we're going to take a look at, and some of the easy crashes and some of the more difficult crashes. You can download the tool, including the source code, from the URL that you see. And when you launch Not My Fault, which I'm going to show you running in a VM, the first thing it does is load a helper device driver. Now, the name of the helper device driver, if I gave it to you right now, would tell you the reason why the executable application is called Not My Fault. It's called Not My Fault actually for a couple reasons. One, if you crash your system using this tool, it's not my fault that you crashed your system. But really, the reason that it's called Not My Fault is that the Not My Fault executable image runs in user mode, and because it's running in user mode and it's subject to the memory protection model of Windows, it's not able to directly cause a problem in kernel mode, which is the only kind of problem that will result in a blue screen crash. So the helper driver is called My Fault to represent the fact that it is the one that's actually causing the problem. You simply select which kind of problem you want Not My Fault to exercise here in the GUI. Once you selected it and you press debug, it sends a command into its driver to actually go perform that type of problem.
So now let's actually use Not My Fault to generate the easiest crash for the debugger to analyze. So we're going to go back to the virtual machine, which is running Not My Fault, and the default crash type is the high Urkel fault. This particular crash type causes Mark's driver to allocate a page pool buffer, free the buffer, raise the IRQL or interrupt request level to dispatch level, and then touch that buffer in the pages that follow. That's going to cause an immediate blue screen because Mark's driver is now accessing memory at a IRQL that is invalid, as we described earlier. Pages in memory that are accessed at IRQL dispatch level or above must be physically present. So notice when I press the debug button, we get an immediate blue screen. The blue screen code is IRQL not less or equal, and Windows is currently recording the state of this crash into the paging file. And if you look on the blue screen on the bottom of the screen, it actually points the finger at myfault.sys. So this is a case where we've reconfigured this virtual machine not to automatically reboot. Normally this blue screen text would have painted and disappeared quickly, but this is a crash that even the blue screen itself points to the faulty driver, myfault.sys.
So let's analyze that dump that Dave just created using notmyfault.sys. And this is where you got to pay close attention. So I'm going to go to All Programs, Debugging Tools for Windows 64-bit, WinDebug, File, here it gets tricky, Open Crash Dump.
That is tricky, Mark, because really there's several open options.
Right, there's Open Executable, attached to a process, connect to a remote session.
There's Open Source File on the top.
File, right.
So this is the hard part, would you say?
This is the hardest part of the analysis, yes, right there. Making sure you've selected the right option in the file menu. Open Crash Dump. Now I'm going to navigate to the crash dump. We've saved it off earlier. Here's HierarQL fault. And here you get a choice. It doesn't really matter what you say, just whether it saves the window configuration that you're using and the other settings you've made in the debugger. And there. I'm done, Dave.
That was really hard, Mark.
It was. And look at what the debugging engine tells us. It tells us that the crash was probably caused by myfault.sys, and we know for a fact that this crash was caused by myfault.sys. It was dead on. But let's take a closer look at what it's telling us. First, up here it says use Bang Analyze-V to get detailed debugging information, and I'm going to type that in right now so we can look at basically the internal operation of the analysis engine. And the first output after entering that command is this description of the stop code, which tells us that the stop code D1 that we saw before just as a number is actually driver IRQL not less or equal, one of the most notorious crash dump codes. And it describes that stop code as representing an attempt to make an access to a pageable or completely invalid address at an interrupt request level IRQL that is too high. This is usually caused by drivers using improper addresses. That is precisely what myfault was doing in order to cause the crash. Then it tells us what the various stop code parameters mean. That's not really that interesting though. Let's scroll down a little bit and then look at the stack trace, which it shows us the stack of the processor that crashed the machine at the time of the crash. And we read this from the bottom to the top. Because this is a kernel memory dump, we don't have any user mode stack frames, and this was the instruction that transitioned into kernel mode. We don't see not my faults on the stack. We would see that if we loaded a full memory dump showing the same kind of crash. And the first function executed in kernel mode was ki fast call entry, which then called NT-device IO control file, which called IOP XXX control file, which then called IOP synchronous service tail. And then we ended up right inside of myfault.sys, where myfault.sys performed the illegal operation. The system caught it as a legal trap, and then called KEBugCheckEX. Notice one thing here. Warning, stack unwan information not available. The following frames may be wrong. This message the debugger prints out whenever it runs across a component on the stack for which it doesn't have symbols. We talked about stacks a little bit earlier, that if the symbol engine isn't present, the symbol information is not present, the analysis engine has to make guesses about where the stack frames are. In this case, it's made some good guesses. MyFault uses standard calling conventions, no tricks, and the guesses then map directly to the stack frames.
Now, by the way, that symbol issue that Mark mentioned, because myfault.sys is a third-party driver, the symbols are not on the Microsoft symbol server. If we scroll back to the very first part of the output when we open the crash dump, one of the first things the debugger did after presenting the bug check code was to complain. Module load completed, but symbols could not be found for myfault.sys. You might look at that error message and think that there was a problem with your symbol configuration in the debugger. That's normal. Any crash that has a third-party driver on the stack, the debugger is going to attempt to load those symbols from the symbol server and not find them. So that's not an error, that's normal because that was a third-party driver.
So let's return to that stack frame, stack trace, and talk about how the analysis engine worked internally. As Dave mentioned earlier, it uses the kind of racial profiling to look at each frame in turn and say, what module is this in? NT represents CentOS kernel, the operating system image file. And the analysis engine looks at this and says, who is this? CentOS kernel. That's us. That's Microsoft. Probably not that. CentOS kernel, not us. CentOS kernel, not likely. CentOS kernel, probably not. Third-party driver, that's probably it. And then it will pick that as the probably caused by.
And it does actually say probably caused
Right.
by, not definitely caused by, because it could have been actually a bug in Windows that called the driver with corrupt data that caused the driver to cause an invalid memory reference.
Right. So this is just guesses, again, until a human sits down and actually analyzes the dump and figures out the precise cause. The analysis engine is forced to just use heuristics and make a guess.
Mark, haven't you also had some other crashes, even on your home system, that the debugger easily solved just by opening the crash dump?
In fact, I did. One of our home systems was crashing periodically. I set it up to generate a crash dump. Unfortunately, I set it up too late. When the crash occurred, it was still configured to generate a mini dump. So all I've got from this particular crash is a mini dump, but it turns out that the mini dump was sufficient for the analysis engine to be able to figure out what was going on. I'm going to go back to the kernel debugger and load that crash dump. And the kernel debugger is going to complain about this mini dump, but it's got enough information there that it's able to analyze it successfully. And we're just going to see a probably caused by pop out here out of the output, which points at a third-party driver, ctodd2k.sys. Turns out this is, when I went to look at the version information on this file, which is on the system, it is the Creative Audio sound driver. And I went to Creative Site, found out, looked at the version that I've had here on the system, looked at the current version that was up on Creative Site, and found that this one was very old. They'd done several updates since this one, downloaded the new version, and the crash has disappeared. So the analysis engine was very easily, quickly able to point at that driver, and that was the root cause of the problem.
I've had similar cases, friends that have sent me their mini dumps. Perhaps now that you've seen how easy it is to analyze a crash, you'll be able to offer that to your relatives and friends. Have them email you mini dumps. They're small attachments, 64 kilobytes for 32-bit Windows, and they'll be impressed when you come back with the probable cause. And it'll just be you and I that know that it was as hard as file, open crash dump, and OK. That's all it takes for simple analysis of easy crashes.
Unfortunately, many crashes aren't as easy to analyze as the ones we've taken a look at. Some, the memories just become too corrupt by whatever problematic driver is corrupting the system, or some hardware problem. More commonly, though, a victim crashes the system, not the culprit. So one driver might have a bug in it where it overwrites the memory that's used by other drivers of their operating system themselves. And it's not that driver that ends up tripping on the corrupted data. It's the driver or kernel that is referencing that corrupt data at a later point in time. So that kind of crash is one of the most difficult to analyze. Unless you catch the culprit making the corruption, at the time of the crash, the finger's going to be pointed at the guy that tripped on the problem, not the guy that made the problem. So we talked about earlier, if you analyze a crash and the analysis engine points the finger at one of the core Windows components like CentOS kernel, Win32k.sys, NTFS, you've probably got what's considered an unanalyzable crash, one that's going to take some extra steps to transform it into an analyzable crash. Another example of what unanalyzable crash is one where you're getting consistently getting different crashes. So you open them up, the analysis engine points the finger at this guy one time, the next time you crash, it points the finger at a different guy. You probably got an example of memory corruption that is causing different drivers or the kernel to trip on it at different times.
So if you've got any of these cases, crash dumps that are not easily solvable, your goal is not to try to analyze these crashes, but rather to turn these crashes into ones that the debugger can easily analyze for you.
Back during the development of Windows 2000, Microsoft recognized that Windows was getting a bad rap because there were lots of third-party drivers out there causing problems and causing people's machines to crash. When an end user's machine crashes, they don't say, hey, it's this Creative's fault or this other third-party driver's fault. It's Microsoft's fault. It always looks like it's Windows. So Microsoft developed a tool called the Driver Verifier to help driver developers outside Microsoft as well as internally to improve the reliability of their drivers. The Driver Verifier is built into every version of Windows from Windows 2000 and up, including even home systems. It's not visible to you generally because there's no shortcut to it. You have to know it's there, and then you can get to it with the run command in the start menu. This tool is one of the most underrated, underpresented tools in Windows because it's so good at transforming what are considered unanalyzable crashes into ones that are very easy for the analysis engine to look at and make a call on.
In fact, in our classes, Mark, we often ask when we get to this point, how many in the room have heard of Driver Verifier? And frankly, in most classes, nobody's heard of it. It really should be in the start menu in the administrative tools, along with things like the performance monitor and the event log, because it is a key tool if you're having spurious blue screens to turn those blue screens into ones that the debugger can easily analyze.
And the Driver Verifier really should be credited as one of the efforts that Microsoft made to improve the reliability of Windows, and more than anything else had the biggest impact on the reliability improvements in Windows. And now Windows isn't known as an operating system that crashes as it was back in the NT4 days before driver developers had a tool to help them find tough-to-find problems in their drivers.
So let's take a look at Driver Verifier. So I'm going to go to the Start menu, and I'm going to run verifier.exe. Again, it's part of Windows. It's not a separate install. And if you're on XP or later, it comes up with a wizard-style interface. Windows 2000 had a tabbed interface that you had to go select the right property pages. On XP and later, it has a wizard-style interface, and the default task is to create standard settings. We don't want to choose that default. We want to choose create custom settings. Now it says for code developers. That really should say for code developers or systems administrators, because it's Driver Verify that you're going to use to enable various checking functions to turn crashes that are unanalyzable, hopefully, into ones that are simple to analyze. So always start with create custom settings, click next, and then instead of choosing the standard settings, again, we're going to make our own choice and choose select individual settings from a full list, click next, and basically at this point, you're going to enable every option in the list except for low resource simulation. So we're going to choose special pool tracking, force Urkel checking, IO verification, enhanced IO verification, deadlock detection, DMA checking, and disk integrity checking. Now, if you're on Windows 2000, some of these items won't be present because Driver Verifier has evolved each version of Windows. Additional verification options have been added, again with the goal of trying to shake out bugs in kernel mode code. The reason that you don't want to enable a resource simulation is that's a special option in Driver Verifier that is really of interest just to a driver developer themselves that causes the system 7 minutes after the system reboots to start randomly failing requests by the driver to the operating system to allocate kernel memory with an error message, a return code back to the driver that says there is no more kernel memory, when in fact there's plenty of memory. So it's there for a driver writer to be able to exercise error paths in the device driver in the difficult to test condition of running out of kernel memory. So that's the option you'll never want to check. Otherwise, check them all.
Now these options, let's just spend a second and talk about some of the key verification options here. One is force IRQL checking. We talked about dispatch level as being one of the special IRQLs where drivers now, the scheduler's off, so drivers are not able to access paged memory. And that's a type of bug that a driver can have in it that can ship out into the field without the developers ever finding it, even if they are very careful about stress testing their driver under lots of situations. Consider, for example, a driver that touches a piece of paged memory. The IRQL is currently passive level. That causes the memory manager to bring that data into physical RAM and connect it to that paged virtual address. Now the driver performs an operation that causes the RQL to go up to dispatch level and then immediately references that same paged buffer again. For that to show up as a bug that's caught by the operating system would take, in that tiny amount of time, that few instructions between the first reference, the IRQL raise, and that second reference, for the memory manager to decide that that page should be reused or sent out to the paging file. Something that's extremely unlikely, even under big stress test configurations. So what that forced RIQL checking does is anytime a driver that's being verified with that option on does something that causes the RIQL to move to dispatch level or higher, the memory manager takes all the pages that are what's called part of the system working set connected to paged pool virtual memory and disconnects those physical pages. So now if the driver goes and accesses that buffer again at dispatch level, it's going to generate a page fault because the memory manager is going to have to go and fix up the connection between that virtual memory and that physical memory. It's at that point the memory manager will look and say, what's the current RQL? Oh, it's dispatch level or higher. Well, that's illegal and it will crash the system. And that's exactly what you want. You want the driver to get caught red-handed, not to perform some illegal operation that's going to end up crashing the system on some end user's machine or in some uncontrolled environment. You want to know exactly what driver has those kinds of bugs. The other verification options work similarly of doing extra checks.
So for example, we're going to be covering special pool, which is an option that will help catch buffer overflows. Pool tracking is an option that really is more of interest in dealing with memory leaks in drivers, and that's a topic covered in our memory troubleshooting video. Mark covered for circle checking. I/O and enhanced I/O verification causes the operating system driver verifier code to do some rigorous inspection of the data structures that a driver is passed and passes back to the system. That data structure is called an interrupt request packet, or IRP. And that data structure has some special rules. It has to point to valid structures. It has to have a consistent set of values. So the driver verifier will inspect that packet after the driver has operated on it to make sure that it's still in a consistent state. If we return back to driver verifier, after selecting the verification options, you click Next, and now verifier wants to know which drivers to verify. What should we pick, Mark?
Well, we're going to give you a recipe for translating unanalyzable crash into an analyzable one using the driver verifier. What you don't want to do is select the option that automatically select all drivers installed on the computer. That's something you want to stay away from. And there's a couple reasons for that. First of all, when a driver is being verified, the system's doing lots of extra checks as it operates. And if you were to have the verifier pointed or turned on all drivers on the system, the performance of your system would basically go to zero. It'd become unusable. So your boot would take 10 or 15 minutes, orders of magnitude or multiples longer than a normal boot process. And if you're troubleshooting problems that are in a production system that are occurring intermittently, you want to get some use out of your system. You don't want it to be unusable while you're hoping that a crash shows up. So what you want to do is go to either select unsigned drivers or select named drivers from a list. And we're going to tell you and shortly, following the recipe, exactly which of these steps you should pick under what circumstances.
Now it is interesting, Mark, that the default radio button was automatically select unsigned drivers, and it's kind of reasonable that driver verifier suggests that, because if a driver has not been signed by Microsoft, it hasn't gone through some basic quality checks, and it's likely, if you're running verifier and having crashes that aren't solvable, that it's probably one of the unsigned third-party drivers.
But guess what one of those quality checks is? When a vendor sends their driver into Microsoft for them to get the signature, to get the signing, it's running the verifier.
In fact, this is another thing that's kind of disappointing in our live class, in our 5-day internals and troubleshooting class. One of the labs we have people do is, although we don't recommend it on your production systems, we tell everyone, okay, now set driver verifier on all the drivers on your system, click Next, and reboot. And the interesting question is, how many computers reboot?
And there's always a significant percentage that don't. There's lots of people that are still running around with drivers that have not been digitally signed or that have been signed and have slipped through testing even with the verifier on at Microsoft.
So that's a pretty sad state of affairs. If a driver can't even boot with a verifier on, then the vendor really has not done their homework. So it's an interesting test you might want to do on your own or on a test system. enable verifier on all drivers. Just see if you can reboot and actually log in as a quick driver quality check. Now, going on to the recipe, the first choice that we recommend is not unsigned drivers, but rather suspicious drivers. So you probably have some idea of the driver or drivers that might be causing the problem. Some specialized hardware devices that you know are on the system, or maybe a driver you've recently updated, or perhaps a driver that's known to be problematic. We won't point any fingers, but some vendors have maybe not the best reputation for the quality of their drivers. So if you go back to Driver Verifier and choose the Select Driver Names from a list, the last radio button, click Next, then Driver Verifier loads the currently defined and loaded drivers. That's an important point, because at this step, Driver Verifier is not presenting in the list drivers that are defined on the system but not currently loaded. So there could be a driver that's problematic that is going to be loaded when a device is inserted. So there's a button that you can see right in the center of the display that you can press, Add Currently Not Loaded Drivers to the list. That will cause Driver Verifier to refresh this list, adding other drivers that are defined in the registry but haven't currently been started. Now you can sort on these column headers. For example, you could sort by the provider, and now scroll through and take a look at the drivers that are not from Microsoft as a quick way to do an inventory, and select the ones that you plan to verify. So after selecting the suspicious drivers, enabling verifier on those drivers and rebooting, if the system doesn't crash, then you need to take the next step. And the second step we recommend is to verify either all your third-party drivers or all your unsigned drivers. As a last resort, if that still doesn't generate a crash that's easily solvable, then you need to start verifying all of the drivers. But for the reasons Mark explained, the performance impact is too severe, so we recommend choosing groups of drivers, maybe 10 to 20 drivers at a time, enabling verifier, rebooting, running for a while. If not, take the next set of 10 or 20 drivers, and so on.
Even if you're not concerned with performance, there's another reason to just go after batches if you're targeting all the drivers, and that is special pool. That's a verification option we're going to take a closer look at shortly that relies on unlimited operating system resource. And if you point all the drivers, verify all the drivers, and you turn on the special pool option for them, special pool is going to run out, and you're actually going to be limiting the effectiveness of the verification process. We're going to take a look at two examples of using the verifier to turn not my fault unanalyzable crashes into ones that are as easy to analyze as the crash we've already taken a look at.
The first one is the buffer overflow. This is kind of a fun experiment to try, because when we invoke the not my fault program to send the control request to the myfault.sys driver to perform a buffer overrun, Mark's driver is going to allocate a buffer from kernel memory and then write past the end of the buffer. And that's going to corrupt whatever memory happens to be following, as you can see in the diagram. So when we go and press the do bug button, some random buffer is going to be overwritten in kernel memory. That may or may not crash the system right away, because it's not until somebody references that corrupt memory that a system crash might occur.
So there could potentially be a long delay between the corruption and the crash. Consider, for example, a driver that's constantly operating in your system, and it happens to have some bug in it that gets triggered one afternoon, just depending on the way that the operating system's using memory and what drivers are running at that time. And that bug causes it to corrupt a buffer related to your CD-ROM burning driver. And a few days later, you pull out a burnable CD, stick it in the machine, and try to burn a CD. The CD-ROM driver activates at that point and goes to read this corrupted buffer. And because it's corrupted, because its data is no longer containing what it expected to find there, it causes an illegal operation. The system detects it, causes KE bug check EX. You get a crash. You open up that in the kernel debugger. You do the analysis, and it points the finger not at the driver that caused the corruption, but at your CD-ROM burner driver, which is just the hapless victim.
So let's now go cause a buffer overflow or buffer overrun. We're going to run not my fault and select the buffer overrun option and press the do bug button. And again, that's going to allocate a non-page spool memory buffer and write a string past the end of the buffer, corrupting the pool header and the data structure that follows. So we're going to go over to VMware and select not my fault, choose the buffer overflow, and I'm going to press do bug once. The system is still up. It's sick, but it doesn't know it yet. Some buffer's been corrupted. Let's press do bug again. Still no crash. A third time. A fourth time. A fifth time. 6, 7, 8, 9, 10. We now have a very sick kernel memory, folks. Nobody's detected it yet. Now I'm going to go, just as an example, try to launch an application that is going to cause the operating system to be exercised beyond what it is right now. I'm going to run Internet Explorer. And let's just see if Internet Explorer makes enough references to the operating system for the detection of the fact that kernel memory has been corrupt to crash the system. Here we go. Double-clicking on Internet Explorer. No crash. Okay, let's go corrupt some more kernel memory. Do bug, do bug, do bug. 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25.
Wow, that's a lot of corruption going on there.
Windows is just really robust and reliable, I think. Again, nobody's tripped on the corruption. Let's try running, for example, Windows Messenger.
There we go.
Blue screen. Now, is it Windows Messenger's fault? Obviously not. Finally, something occurred that caused some software in kernel mode, not Windows Messenger, but something that was invoked indirectly to cause the system to crash.
So when the kernel detects a corrupt pool, what you'll see on the blue screen is a message about turning on the driver verifier. And it tells you what happened, but not why. Let's go take a look at the crash that Dave just generated in the kernel debugger and see what the analysis engine shows us. So open crash dump. And the one we're taking a look at is right here. And there's BugCheck C5, which appeared briefly on that blue screen that we saw. Let's do an analyze-v to see what C5 means. And it tells us driver corrupted executive pool. That's what the EX stands for. An attempt was made to access a pageable or completely invalid address at an error request level that was too high, usually caused by drivers that have corrupted the system pool. Run the driver verifier against any new or suspect drivers, and if that doesn't turn up the culprit, then use gflags to enable special pool. It turns out that that last suggestion there is not necessary, as we'll see the driver verifier itself turns on special pool.
Now, by the way, Mark, if we go back to the top, the probably caused by, when you open the crash dump, was some poor innocent victim.
Right, RAS ACD, which is a core Windows component.
So this is a classic example of you have a crash, the debugger is pointing at a Microsoft supplied driver, your assumption should be that it wasn't that driver's fault.
And if we look at the stack, the analysis engine basically said NTOS kernel, probably not, came across RAS, looked at the rest of the stack and only found NTOS kernel, and up here a reference to the hardware abstraction layer, DLL, HAL, and it has internal weightings. These components are so core, the HAL and the kernel, that it gave a lower weight to this and basically said it's probably RAS. If I had to pick out of those three there on the stack, I'd go with RAS, and that's where it came up with the probably caused by.
So you'd say the operating system was kind of proud because that's the last assumption is that it could be its fault. It has to be somebody else's fault.
And if there's only the operating system on the stack, at that point it'd be forced to say, well, I guess I did it.
Now, that buffer overflow crash we generated was an example of really an unanalyzable crash. Without somebody having the experience of looking at memory patterns that could detect, looking at the buffers that were being accessed that were a signature that they would be able to trace back to the driver, it's effectively, for our purposes, unanalyzable. Let's notice the difference, however, when driver verifier is enabled on Mark's myfault.sys driver, and we're going to see that in that case, the driver is caught in the act of corrupting the kernel memory, and the blue screen is going to point right at the culprit driver. So we've resumed a virtual machine with driver verifier enabled on myfault.sys, and we can see that if we go and run verifier in the virtual machine. And I'm going to choose the option to display existing settings, click next, and we've enabled on a system-wide basis, not just for Mark's driver, all of the driver verifier options except for the one we said never to enable, a resource simulation. So verifier is on actually for all the drivers on the system right now. So let's go back to not my fault, and choose the buffer overflow. Now at this point, when I press the do bug button, the driver is going to attempt to write beyond the end of its allocation, but be caught exactly in the act. Here we go, pressing do bug now. Instant blue screen. And if you look at the blue screen text, It says on the top, the problem seems to be caused by the following file, myfault.sys. The driver is attempting to access memory beyond the end of the allocation. And this is driver verifier catching a driver in the act of performing an illegal operation.
Let's go take a look at the crash dump file for that. So I'm going to go to Open, Crash Dump, and select Buffer Overflow Special Pool, which is the crash that was generated when the verifier was watching. And the analysis engine is going to look and tell us a lot of the same information that we saw on the blue screen. Now remember though that in most situations you'll never see the blue screen, so you'll never see myfault.sys there or that text that came out. But right there it tells us probably caused by myfault.sys. If this were the real world analysis, we would be done. And we know for a fact that it is myfault.sys that caused this. Let's just take a look at the stack. If we do a bang analyze -v and look at the message, the description of that stop code, driver fault beyond end of allocation, n bytes of memory was allocated, and more than n bytes are being referenced. This cannot be protected by try except. When possible, the guilty's driver name is printed on the screen. And if we go down and look at the stack, it's going to look familiar at this point. If you looked at the stack for the easy to analyze crashes, because myfault.sys is sitting there right on the stack, being called from the kernel, passing the I/O control from the not my fault GUI right into the driver where it honors the command to corrupt memory and gets caught in the act by the verifier. Let's talk for a second about how the verifier knew that this driver was corrupting memory. The verification option that triggered that is the special pool verification option. When a driver is being verified with the special pool option on for it, Windows tries to satisfy memory allocations for it from a special region of memory, hence the name special pool. This region is special because every other page in this region is an invalid page of memory. And it aligns driver buffers against the top of the page from which it allocates the buffer, so that when the driver goes marching off the end of its buffer, it doesn't end up sitting in somebody else's buffer, like the pool data structures or another driver's buffer. Rather, it ends up touching one of these invalid pages of memory. And the mere fact of it touching an invalid page of memory triggers a page fault. The page fault handler looks to see what's being referenced, sees it's an invalid page of memory being accessed from kernel mode, and will immediately crash the machine and tell you that it's a problem with the driver trying to access invalid memory. Caught right in the act, which is exactly what you want. Driver verifier to the rescue. Transformed, unanalyzable crash, causing corruptions, causing random drivers to be blamed into one that looks like our easy to analyze crash.
Now, as Mark mentioned, there are a couple of conditions. Even if you've enabled special pool on a particular driver or system-wide, allocations that are sent to special pool have to be of a size less than 1 page, which is on an x86 platform and x64, 4 kilobytes. So when a driver allocates a large memory allocation, that's not going to come from special pool, which means if it overwrites that buffer, it's not going to have the protection and the check that we just saw occur with the Not My Fault demo. Special pool happens to be one of the driver verifier options you can enable without requiring a reboot. Most of the others do require a reboot. And keep in mind that it's a limited resource, so when special pool has run out, drivers that are being verified are going to have their pool allocation sent to the normal pool, and that's not going to have that protection that we just described enable for that driver.
Let's take a look at another example. And this example, Not My Fault implements, it's the code overwrite example. And code overwrite happens when a driver has a bug in it that corrupts a pointer, and that pointer ends up pointing into the code of the operating system kernel or other boot start drivers. Most of the time, this kind of access won't be detected. Sometimes it will. And let's talk about the situations where Windows recognizes that a driver is trying to overwrite part of the code of the operating system or another driver. And for that to occur, Windows has to have some facility on called System Code Write Protection. System Code Write Protection is the mechanism by which the memory manager marks the code pages of the operating system and their drivers that are loaded as read-only, so that when a driver tries to write to those pages, that triggers a page fault and the memory manager will crash the system with a stop code that indicates that a driver tried to modify code. However, most of the time that system code write protection feature is turned off for performance reasons. Windows, in order to save space in the precious translation look-aside buffer that's on a CPU as a cache to map virtual addresses to physical addresses, will map the operating system code and boot start drivers into a single large page of memory, which is on x86 and x64 4 megabytes in size. The standard page is 4 kilobytes in size. And an image, like a driver or the kernel, is defined in 4 kilobyte segments where code and data are within the image. If the operating system loads an entire image with both code and data pages in it into one of these large 4 megabyte pages, it has no choice but to set the memory protection on that large page to read-write. Otherwise, the kernel or drivers wouldn't be able to modify their own data that is also mapped into that large page. The conditions under which the system uses large pages as the performance optimization are that the machine has more than 127 megabytes if it's running Windows 2000, or if it's running Windows XP or Server 2003, that the system has more than 255 megabytes. So in other words, almost all the time on systems today, system code write protection will be off by default.
Now, there is a way in the registry to explicitly turn on system code write protection, but you don't need to do that because when verifier is on, even on the most minimal settings on a single driver, system code write protection is enabled. So when you turn on verifier, the kernel is going to be mapping itself and the drivers with small pages, and therefore an attempt to write to a piece of code will generate an immediate blue screen. Let's go watch what happens on a system that does not have kernel write protection on. So in other words, the default case, by going back to not my fault. So we're going to go back to the virtual machine and we're going to select the code overwrite option. Code overwrite causes Mark's driver to overwrite the first few bytes of a very frequently accessed system call, ntread file. That's the underlying system call that is called on behalf of a thread that goes to read from any file handle. So that's going to be called very, very frequently on most systems. So when I press the debug button, that code is going to be overwritten. Again, that's permitted because this is a default system that has the kernel and the boot start drivers mapped in a large page that's marked as read-write. But it's going to be very, very quickly detected because somebody else is going to make a call into the ntread file function, which is going to run into garbage instructions and cause a crash. So here we go. I'm pressing debug, and the system crashed. If we look at the stop code, there's no pointer to the driver at fault because the driver that caused the code overwrite is long since gone. Let's go take a look at that dump, shall we, Mark, and see what we could learn from it.
Let's take a look. So I'm going to go back to the kernel debugger and go open the crash dump, code overwrite. And let's see who the hapless victim was this time. So this is actually from a different different crash than the one we just saw. You can see the bug check code is different, so that tells you right away that code overwrite like this can generate different types of stop codes. It also points the finger at Win32k.sys, one of those core Windows components that if the analysis engine ever points the finger at it, you should just simply not trust. You should believe that you don't have a valid analysis. But let's take a look at an analyze-v and see why the system picked that and what the stop code that generated that crash tells us. Kernel mode exception not handled, AD. This is a very common bug check. Usually the exception address pinpoints the driver or function that caused the problem. Always note this address. Well, we don't even have to read the rest because we know that this is a misdiagnosed analysis. And if we look at the stack at the time of the crash, well, it turns out that it's actually Win32k.sys that ended up somehow causing the execution of the overwritten code and getting blamed for the crash. So a failed analysis. And what we need to do is, again, turn to the driver verifier.
So let's go back to a virtual machine that we've now resumed that has verifier turned on. Because verifier is on, system code write protection has been enabled. Now we're going to choose code overwrite, and this time when I press debug, the driver's attempt to modify the code in the operating system will immediately be caught because it's attempting to write to a read-only page, whereas in the previous example, the memory that it was trying to write to was read-write. So I'm going to press debug. Instantly the system crashes, but if you look at the blue screen text, we have a little more detail. Right at the top it says, the problem seems to be caused by the following file, myfault.sys. So now we know the driver that was at fault. And the second line below that shows the reason. An attempt was made to write to read-only memory. So driver verifier, because it enabled system code write protection, caused this kind of bug, a code overwrite, to be caught dead stop in its tracks, pointing to myfault.sys. Shall we go open the dump?
Let's go take a look at that crash dump and see what the analysis engine has to say about that. So open crash dump, code overwrite with write protection enabled is the name of the dump. And what comes out? Bug check BE, probably caused by myfault.sys. So the analysis was dead on accurate, and let's take a look at what that BE is and what the stack looks like. BE is, as was described on the blue screen text, attempted write to read-only memory. An attempt was made to write to read-only memory. The guilty driver is on the stack trace. So it's right there telling you how it figured it out. And if we look at the stack trace, this is getting to be old at this point because it looks just like our easy to analyze stack traces from the earlier example and from the examples we've had where we've turned on the verifier. Not my fault is called into the kernel. The kernel is called into myfault.sys. Myfault.sys has performed the code overwrite and got caught right as it was trying to modify the kernel memory. The system crashes and points the finger right at it.
And that stack, by the way, interesting that we can see the caller of the KE bugcheck-ex function. That's the function, remember, that the operating system or drivers call to crash the system was actually called by the memory manager because it was the memory manager that got invoked to handle this invalid memory reference, the attempt to write to the read-only memory. It's the debugger's stack analysis engine that looked at this stack, and although the memory manager was the direct cause of the crash, the culprit pointed to is the third-party driver myfault.sys.
So just to summarize, we've made you Crash Dump Analysis pros simply by the fact that we've told you about the verifier and told you how to enable it using the Crash Dump Analysis recipe to get the best performance out of your system, to get the maximum effectiveness out of the verifier and its special pool option in order to turn unanalyzable crashes into ones that are very easy to analyze just simply by going to open crash dump in the kernel debugger.
Sometimes you're going to be faced with crashes that, even using driver verifier, aren't yielding easily analyzable crashes. For example, you open the crash dump and the debugger points to a different reason each time, a different driver. Or memory may be too corrupted to even perform this basic analysis. So in that case, you are going to have to open the crash dump and perform some manual analysis commands that we're going to describe in this section.
Now, some of the commands that are useful for looking for hints as to what might have caused the problem include just looking at the stack of the current thread at the time of the crash. I'm going to open a crash dump file up here, one from the easy to analyze crash dump, and just demonstrate some of the commands that you would be executing in the situation where you've got one of these unanalyzable situations. So the analysis engine is going to actually say something, but kv is the command that you would use to look at the kernel, the stack of the current thread. In this case, it tells us right there that this driver caused the problem. The reason why you want to execute this command is that the analysis engine might have misdiagnosed it and pointed the finger at another driver that's on the stack, whereas you look at the stack and you recognize that, hey, there's a driver that's related to something I just did, something that I just installed, and that might be the driver that's caused the problem.
So basically, you need to perform your own racial profiling.
Right.
The debugger might have pointed to a Microsoft driver, but if you look further back on the stack, perhaps there is a third-party driver. Or maybe you have a number of crashes that are pointing to different drivers, but the stack has something in common. There's a consistent third-party driver somewhere on the stack of each of those crashes.
Another thing to do is to type lmkv, and this command dumps the list of currently loaded drivers, along with version information for them if it's present in the physical memory of the dump. And in this case, LMKV tells us the versions of many of the drivers on the system, including third-party drivers, like here's one from sysinternals. And the reason this information can be useful is for you to make sure that, first of all, you understand the purpose of every driver on the system, especially if this is a production server. You want to make sure that you know that only the essential drivers are present and running on the system. You don't have unnecessary things that could be causing instability. And second, you check the version numbers, like the file version and product version. Go to the vendor site for the particular driver and make sure that you've got the most recent versions. Vendors are always releasing updates that include fixes. You want to make sure that your server or even your client is running the most up-to-date drivers.
I got a story there, Mark, where just that single command helped me solve a series of dumps that were pointing to different drivers every time. Did an LMKV, did a little inventory of the drivers loaded on this system, and there was one third-party driver that was a sound-related driver that was a very old version, the timestamp, like the one that you see on the screen here, Mark's Control to Cap driver 1999. Well, we know that you haven't updated that in a long time, Mark, so this is the latest version, but that is a fairly old date to see on a modern system. So we went to the vendor's website. Sure enough, there was an updated driver, loaded that driver, and the crashes went away.
Mm-hmm. Another command that might be useful is the bang VM command. And the bang VM command actually dumps the amount of physical memory, including non-page pool and page pool, currently outstanding on the system, including the maximum values of those different pools. So if your pool usage for either page pool or non-page pool is close to the current or close to the maximum or at the maximum, then you might have a leaky driver. And that leaky driver could have exhausted one of these resources, and that will almost certainly lead to a problem at the minimum instability and most likely a crash of the system.
Now, if that's the case, the command mentioned on the slide is the bang pool used command. Bang pool used uses information that the operating system, if you're running Windows Server 2003 and later, captures by default. Earlier versions of Windows, XP and earlier, do not have this pool tagging option on. That can be enabled with the gflags tool, gflags.exe in the support tools. So if pool tagging is on, you can use bang pool use, which sorts through the kernel memory pools and displays the usage of the pools using a summary code, a 4-letter code that each driver passes to the operating system when allocating memory to give a unique identifier called the pool tag. Pool tagging, again, you need to enable on XP and earlier, allows the operating system to keep track of the names of the memory areas. The hard part is then mapping that pool tag back to the driver. As a start, if you look in the debugging tools directory, in the triage subfolder, there's a pool tag text file, but that only has the Microsoft register drivers. So how can you find a pool tag that is used by a third-party driver? It requires using an advanced sysinternals tool, strings. And strings is a tool that opens a file and dumps the printable string. So at this point, you're kind of grasping for straws, hoping to find the driver on your system that has the string used for the pool tag. So the strings tool can be used, for example, to dump all the drivers in the Windows System 32 drivers folder. You could pipe the output to the find SDR command, specify the pool tag, and hope to find the driver that's using that pool tag.
An easier way to track pool leaks would be to use the verifier. One of the options is pool tracking, as Dave pointed out a little bit earlier. And when you select pool tracking, the system, the verifier, keeps track of the allocations by driver. So instead of by tag, it does it by driver and then presents you a drop-down list if you run the verifier and look at the information about currently verified drivers. It will show you how many outstanding pool allocations of non-page pool, page pool there are by driver. So you can use the verifier then to go and monitor the drivers for leaky behavior. Speaking of the driver verifier, if the driver verifier crashes your system and it tells you that it detected a deadlock, the bang deadlock command is something you can enter to get information, to have it look at the situation that led to the deadlock situation or the hang, and point the finger at the driver that may be at the root cause of the deadlock problem.
Now, if none of these manual analysis commands point you to the culprit of the crash, here's a couple of other things you could look at that are starting to be a little bit of a reach in terms of helping you to identify the cause of a crash. And one is to examine the currently executing thread with the bang thread command. Now, the currently executing thread may or may not be related to the cause of the crash because, as we've discussed, drivers could be running at a high interrupt level, interrupting some currently running thread. If the crash occurs inside a driver's interrupt service routine, the thread that was currently running at the time of the crash is not really related to the cause of the crash. It was the innocent victim. It happened to be the running thread. It was interrupted by driver code that caused the crash. Another command you might try is the bang process 00. I'm going to go over to the kernel debugger and show that. Bang process space 0 space 0. This does a summary level display of the processes that are active on the system at the time of the crash. What might you be looking for here? Well, just like the lmkv command could be used to make an inventory of the loaded drivers, this would be a safety check. Do I recognize all the processes that are active on the system at the time of the crash? Is there something suspicious in the list, or something that's present on a series of crashes that seems to be a common thread? Maybe that's an application that you know talks to a particular hardware device, and that might then point you towards the device driver that could be at fault.
We're going to take a look at an example you can generate with Not My Fault that generates an unanalyzable crash that remains unanalyzable even if you turn the verifier on all settings and point it directly at the myfault.sys driver. This example is what's called a stack trash. And a stack trash happens when a driver ends up overwriting its stack. As we've seen, the stack is one of the core resources that the analysis engine uses in trying to determine the cause of a crash. It's where it aims its heuristics. So if the stack has been corrupted, the analysis engine really has not much to go on. And how likely is it that you run into a stack trash in the real world? It's actually not too unlikely that a driver will overflow its own stack or have a buffer on its stack that it ends up writing past the end of, just as we saw a little bit earlier when we took a look at the buffer overflow example. If that buffer happens to be on the stack, then you'll end up in the same kind of situation, but the verifier won't catch it. As far as overflowing the stack, the kernel drivers have a very small stack. It's 12 kilobytes by default on x86 systems. Not a whole lot of space to store stuff, and if a bunch of drivers call each other and they end up using up that space, you'll get a crash and the stack has been overflowed, and again, a difficult to analyze crash dump scenario. The kinds of symptoms that are exhibited by stack trash are crashes that end up showing you stop codes like K-mode exception not handled. K-mode exception not handled happens when the system just goes and tries to execute garbage as if it were code. And since, as we're going to see, the stack is corrupted, you're not going to get much out of the analysis.
So let's go cause a stack trash crash, and then we'll go take a look at the dump that's generated.
That rhymes.
Stack trash crash. So I'm going to go over to Not My Fault, choose the stack trash option, press debug, and Mark, what exactly is your driver doing when I select this option?
It allocates a buffer on the stack and simply overwrites it by, say, 30 or 40 bytes. So enough to overwrite the return address, so when the function tries to return, the system's going to go off into the weeds.
Let's see what happens. Here we go, pressing debug now. And this was an interesting one. Frozen.
It's hung?
It's a hard hang. Shall we try one more time? Let's resume the virtual machine. And go resume the snapshot. We'll try this one more time. Okay, going back to Not My Fault. We're going to select stack trash, press debug, blue screen this time. So in the first case, return to some code that didn't even allow Windows to record the fact that there was a serious internal error. There was no blue screen. That's a case that we're going to be discussing later, how to analyze systems that are having either hangs or spontaneous reboots that don't generate a crash dump.
Now let's take a look at that dump that might have been generated. And again, this is just one of many types of dumps that could be generated from that one particular example. So the dump you get on your system, if you try Not My Fault, might look different than what I'm seeing. Let's see what the analysis engine does with the corrupted stack that it's been given here. Well, stop code 8E, probably caused by NT kernel PA, which is the large memory version of the operating system kernel.
So this is actually something that pains the debugger very much. It finally had to blame the Windows operating system kernel.
It felt it had no choice. And let's see why it felt it had no choice by doing the bang analyze-v, looking at the stop code reason. First of all, up here, kernel mode exception not handled, very common bug check. Let's scroll down and look at the stack trace. and what we see is nothing but the kernel in that stack trace. So the analysis engine, its heuristics, looked at it, tried to find somebody who could pin the blame on, somebody else, and finally gave up and said, all right, I guess it's us. So now, where do you go from here? Let's say that you've been having you have a server that's crashing intermittently. You look at the stack trace, you look at the dumps that are coming out of it. It's always pointing the finger at NTOS kernel, NTFS, Win32k.sys. You get desperate at this point. After you follow the crash dump analysis recipe, you've got the verifier, you've take a look at all the drivers. Now it's time to just poke around using some of the kernel debugger commands to see if you can figure out what might be the cause. Again, just a hint to go off of. So I'm going to type bang thread, and this shows us the currently executing thread on this processor at the time of the crash. What I'm going to do is rely on some advanced internals information, just to demonstrate how you can put together various kernel debugger commands, get some experience with this, and try to reach for a clue.
By the way, without even looking at this data structure, Mark, the bang thread command, if we look on the right side of the screen, does indicate the process that owns the thread that was executing. So this stack trash crash, which the debugger couldn't analyze, by using the bang thread command, we see that we were running a thread inside your Not My Fault program. So we kind of got the answer just looking at that. But let's take a look at that IRP.
Okay. So I'm going to use the bang IRP command to dump the contents of that IRequest block. And one of the things that the bang IRP command tells us is what driver this IRequest packet was aimed at. In this case, it was aimed at my fault. And does this prove conclusively that my fault was the cause of this crash? No. Is this a hint that maybe we should go investigate myfault.sys and see if it might be involved with the crash? Make sure for certainly if we've got the most recent version? Yes. And also make sure that we absolutely need it on our server. If possible, try running the server without it and hope that the crashes go away and are caused by it. So that's just an example. Again, every situation is going to be different. Every crash is going to be different. So it's a matter of poking around, seeing if you can get a clue.
What do you do if you have no crash dump to analyze? We're going to look at several ways that you can get control of the system at the time of a crash or a hang so that you can try to perform some analysis in the case when there's no crash dump generated. And the key is booting the target system, the system that's having difficulties, in debugging mode. That's something that's part of Windows. You don't have to install anything to activate this option. And the way to choose debugging mode, most simply, is to press the F8 key during the boot, which brings up the special boot options menu that you've probably seen before. That's where you can select last known good, safe mode. But in this case, you're going to choose debugging mode. Choosing debugging mode causes the operating system to load some kernel debugger code at boot time that permits you to break into the system if it's hung, or if the system crashes, causes the system to wait for you to connect a host system that can then analyze the cause of the crash or the hang. This doesn't affect performance, but it does have one important effect, and that is when the system crashes, it will not automatically reboot even if you've configured it to do so. So be careful booting a system in debugging mode on a production server, because when it crashes, it's going to wait for you to connect a host kernel debugger so that you can go look at the problem, and it will not automatically reboot, even if it's configured to do so. But that may be your only option. If you're getting crashes, spurious crashes that result in no dump, you'll need to boot in debugging mode and wait for a crash.
Now, just one comment, Dave, before we move on about the F8 switch that you boot the system into debugging mode. That switch causes the system to pick default conservative values for what communications port the kernel debugger is going to talk through and what speed it talks through. Specifically, one of the serial ports at a very low baud rate, 19200, which if you're going to try to connect to a crash system using that kind of speed, you might as well connect, go off for dinner, come back a little bit later and see if you've finally been able to get into the debugger to actually poke around. And even poking around is going to be extremely painfully slow. So I recommend that you avoid F8, that you, where possible, go modify the boot.ini of the system to boot into debugging mode. And newer versions of Windows support IEEE FireWire debugging. Vista supports USB 2.0 debugging. So those are some alternatives that are certainly way more efficient, way faster than debugging over a serial port.
For details about how to configure the kernel debugger and also boot.ini for these various other alternate connection mechanisms or higher baud rates, just go look in the debugging tools help file and you'll find detailed instructions on that.
By the way, Dave, did you know that they call boot.ini the Great Bootini at Microsoft?
I hadn't heard that, Mark.
So let's talk now about what happens after the system's crashed and you've got kernel debugging enabled. What are the next steps? And we've got a system here that we're going to configure to crash during the boot before a paging file is created. So it's a great example of a system that will crash and no crash dump will be generated, where you've basically got no choice but to configure it for kernel mode debugging so that you can connect to it and then analyze it. And I'm going to go modify the configuration for myfault.sys, which has already been loaded because I've run myfault, to load as a boot start driver. And when it loads as a boot start driver, I'm going to change the start value to 0, boot start driver. Now exit and reboot the machine. The myfault driver sees that it's a boot start driver and will perform an illegal operation right then and there. This happens so early during the boot process, before the paging file has been configured, that there will be no dump extracted. The system will simply crash. And if it was configured to do so, it would automatically reboot at that point. So you'd be stuck in an infinite cycle of crashes. What we're going to see is it's going to crash and then show us what's on the blue screen. And if we boot it in debugging mode, it's at that point that we'd pull up a second machine and follow some steps I'm about to show you. So there's the crash. Again, typically we would have seen information down here at the bottom about it writing the information out to the crash dump file, but it simply stops. It doesn't even tell us that it's not able to do that because the paging file has not been initialized yet.
And if you look at the top part, it says a device driver attempting to corrupt the system has been caught. The faulty driver is on the kernel stack. But unfortunately, there's no display of that, and because this was an early crash, there's no record of the crash in a crash dump file. So this is an example where it's unanalyzable without booting the system into debugging mode and gaining control when that crash occurs.
Right. Now just let's demonstrate very briefly the steps that you'd follow in that situation. Instead of going to File, Open Crash Dump, you're going to go to File, Kernel Debug, and then enter the information according to however you've configured the remote system to communicate with this host system. So the machine crashing, the kernel debugging help file refers to as the target. The one you're running WinDebug on is called the host, and what we would do is then enter the appropriate baud rate and the serial port local to the host, type OK, and then it would wait to break in to the remote system. At this point, if you were connecting to a broken system or a crash system, you would press the break key here, and it would try to immediately make a connection with the kernel debugger on that remote system. What you do there is take a look around in the way that you would if you were looking at a crash dump. Basically, you have a crash dump, it's just not been saved to disk. So the same steps we've been following along here, you use on the crashed machine.
So when the debugger connects, it's going to display the reason for the crash. And so do I have to run the debugger on the host system before I boot the target in debugging mode or after, or does it matter?
It doesn't matter. You can basically configure all your servers to crash on, to boot with kernel debugging. When they crash, they'll sit there and wait for you to walk up and connect to it with the kernel debugger and then analyze the crash at that point.
So what some people do is they have a laptop, basically a debugging laptop set up that's got the symbols loaded for the kernels in their network. It's got the debugging tools installed, and they've got a null modem cable if they're going to use a serial port, so that when one of their systems crashes or they're having spurious issues and they need to boot a system in debugging mode, they'll boot in debugging mode. When the system crashes, again, it's going to totally freeze. There will be no blue screen painted. At that point, they'll bring that debugging host machine, laptop for example, to the target machine, connect via the serial null modem cable or FireWire or in Vista USB 2.0, and as soon as you run the debugger, configure it and choose the file kernel debug, it's going to connect, and at that point you can analyze the dump.
One of the things you can do if you're not able to analyze the dump immediately and you want to get the system back up and running again is to save the dump to the host system. And you can do that with the .dump kernel debugger command, where you can either capture a full dump or a mini dump. Be aware that if you try to go capture a full dump and you're doing it over a serial cable, even at the maximum baud rate of 115/200, that you're probably going to be sitting there for on the order of hours, because there's so much data that's going to come across that serial cable. Really, that's something that's only practical if you're doing it over a FireWire or USB 2.0.
But hopefully, the bang analyze -v that you type
Right.
will have solved the crash, and you won't need to save the dump.
Or maybe the mini dump is sufficient for you to be able to hand it to somebody else to take a look at if the analysis isn't able to pinpoint the cause.
Now, that was the case where you have a system that's crashing. It's crashing but not generating a dump. Another case where you have no dump to analyze is when a system freezes or hangs. The system becomes unresponsive. You try to type on the keyboard, nothing happens. You try to move the mouse and it's frozen. Or it's so sluggish that the system is unusable. And there's two kinds of hangs. One is the instant lockup. Something happens inside kernel mode, inside a driver, that causes a kernel synchronization deadlock. System is frozen. Or maybe a driver or piece of kernel code goes into an infinite loop at a high interrupt request level. That is, at a point where the system can't service keyboard or mouse input. Or potentially a very high priority thread begins running that is running at a higher priority than the windowing system's threads that need to execute to send window messages and window input to other normal threads. So that's going to be immediately noticeable because the mouse is not going to move and there's no keyboard response. You also might have the grinding halt. The system becomes slower and slower to the point where there's very, very little responsiveness.
And typically I've seen that where you go to launch an application, that application partially comes up, then you go to say what's wrong, you go to the start menu to launch something else, the start menu opens but doesn't fully paint in, and sooner or later the mouse is going to freeze up and you've got a full hang. So there's a couple of different approaches to troubleshooting a hung system. Both of these require you that you take some steps before you end up with the hang. So if you've got a server that's out there and you haven't done anything, it's hung, there's no way to troubleshoot that. You've got to reboot and hope that, do some preparation, hope you get the hang again, and are ready to go and debug it. The first option is manually configuring the hung system to generate a crash that you can take away the dump for and analyze. And the second option relies on booting the server or the system in debugging mode so that when it does hang, you can walk up to it with a host debugger running WinDebug and connect to it and then take a look around at the hung system. Let's take a look at these options.
So to configure the system to crash from the keyboard, you've actually got to go run the registry editor and add a value documented in the Debugging Tools help file that causes the serial port driver to respond to a special keystroke sequence and cause a system crash. This is documented in the Debugging Tools help file. We're going to go bring that up right now and show you how easy it is to find. If you go to the search tab and search for the word manual and scroll down, search for the word keyboard, we have forcing a system crash and forcing a system crash from the keyboard. And here's the article. And if you look down in the middle part, it refers to the registry value that you need to edit, that you need to add. You can see it under current control set services I8042PRT parameters. It asks you to create a value called crash on control scroll and set it equal to a 1. The crash on control scroll name comes from the fact that the default keystroke sequence, as it says here, is to hold down the right control button and press the scroll lock key twice. That's the magic keystroke sequence to cause Windows, in this device driver, to initiate a crash. One note is that this requires a PS2 keyboard. A system with a USB keyboard is not going to crash with a special keystroke sequence. Also, there's no guarantee that you're going to get a crash because the system could be locked at a point at an interrupt level the same as or higher than the PS2 keyboard driver, which means when you press those keys, they're not going to be processed at all. So configuring this on your systems really is not a bad idea from the start. It's unlikely that a user is going to press the right control scroll lock. And when you need it, you've got to have that done before you boot. But if you are getting spurious hangs, you could configure that option, and then when the system hangs, attempt to do the control scroll lock, and generate a crash.
Another option for causing the machine to crash is to send in a non-maskable interrupt to the NMI pin on the motherboard. This requires a little bit of setup because you've got to go into the registry and configure a certain value that causes Windows to crash when it sees an NMI, or a non-maskable interrupt. And you can again get to that information here about using an NMI switch to configure the system to crash upon an NMI.
Now it says on there, Mark, contact your hardware vendor to determine whether your machine has this switch. So this is something that's vendor specific. Some server boxes in particular have essentially a crash me button.
Right. And most high-end servers do. And even if they don't, you can go and follow directions on Microsoft's website. Go search for NMI on Microsoft's website, and it'll give you directions that if you follow, spend about $10, go to Radio Shack, will allow you to put together a switch with a wire, put it on an NMI pin of your motherboard such that when you press the button, it sends an NMI into the motherboard and causes Windows to crash. It's really kind of fun, pressing a button and having Windows crash like that.
Now, you've tried the first option, the system hangs, you've tried configuring the option to crash the system from the keyboard, but nothing happens. So now what do you do? Well, the other option is to configure the system in debugging mode and then use the kernel debugger to attempt to break in and then go poke around. So this is like the previous case where we talked about a system that's crashing, but it doesn't generate a crash dump. You would boot it in debugging mode. Again, you could either press F8 and choose debugging mode or manually edit boot.ini to add an entry to boot in debugging mode with the proper connection type and baud rate. So in either case, you've booted the target system that's having these spurious hangs in debugging mode. When the system hangs, instead of touching anything on the target, you would bring up your debugger host system, perhaps on a laptop, connect it to the target system using the appropriate mechanism, such as an L modem cable, run the debugger, click on File Kernel Debug, and then when the debugger comes up and says waiting to connect, you're going to force the connection. So you're going to attempt to break in. That's going to attempt to talk to some code that hopefully is accessible and still active on the target system. Even this is not guaranteed to give you control on the hung system because Windows could be stuck at a point that even this kernel debugger communication code can't respond to. But assuming you can break in, then you can begin to poke around and use some of the manual analysis commands we've discussed to see what was going on at the time of the hang.
So just to summarize some of those manual analysis commands you're going to want to perform. First of all, bang analyze-v to see if the debugger engine, analysis engine, can figure out what might be the cause of the deadlock. Look at the stack of the thread running at the time of the crash and use the bang thread stack to look at that. Look at the bang thread stack to also look at the thread that was active. What process is it part of? Use bang locks to look for possible deadlocks. Bang locks is a command that dumps information about certain types of kernel synchronization resources that are commonly used by drivers. So this is especially useful in the case where you've got the grinding to a halt hang. Typically not very useful for the situation where you've got the sudden freeze.
I actually had a server, Mark, that was in that state. It was not totally down, so we could ping it, but it was a file server, and file accesses to the server were hung up. So we broke in with a kernel debugger and did a bang locks command, and sure enough, it pointed to NTFS locks that were being held by the file system driver, and it turned out it was a bug in Windows 2000 for which there was a hotfix available.
One of the things we haven't talked about yet is how to switch the processor context of the kernel debugger. And you do that with the tilde command. For example, let me open the kernel debugger and just demonstrate. Now, we don't have multiprocessor crash dump. Actually, we do a little bit later, but let me just show you the syntax for that command. Let me open a fresh kernel debugger here. Go to local kernel debugging where I can demonstrate the syntax. So this is a single processor debugger. The prompt doesn't have any processor context. If it was a multiprocessor system, you would see the processor number and a colon where the processor number started 0. And if you wanted to switch the context of the kernel debugger, you could type tilde followed by the processor number you're interested in. So 1 would be the second processor on a 2-processor machine. Once you've switched the context, the bang thread command and other commands like bang RQL are processor specific. And so they'll be looking at the state of the processor on which the kernel debugger has its focus. This is especially important or specifically important in a case of a hung system where the hang can be caused by code executing on a processor different than the one that you've broken into. And so you want to be taking a look at what's going on each of the processors on an SMP system in that case.
Now, if you've been able to gain control of the hung system, you've used some of these basic manual analysis commands that Mark reviewed, if you still can't figure out why the system was hung, but you'd like to save its state for later analysis, perhaps to submit to Microsoft, you've got two choices. In the kernel debugger that you've connected to the hung system, you can type .crash. That sends a request to the target system to basically blue screen itself. which will cause it to, if it's configured, to write the dump file, and then the reboot will be extracted. The other option is to use the .dump command to copy the current system state over the kernel debugger connection, which again could be slow on a serial connection, and make a copy of the system state on the host machine. In either case, you've now got some snapshot of the hung system that you could perhaps send to Microsoft for further analysis.
Now we're going to demonstrate an example with Not My Fault of a hung system and then go analyze it. So we've got a VM running Not My Fault, and this hang button down here causes the machine to lock up. So I'm moving around the mouse, but it's not responding. This machine is totally frozen. Beforehand, we've gone and configured the registry, the i8042 port value, to crash on control scroll lock, and then rebooted the machine. So what I'm going to do, I've got the focus in that VM. I'm going to type right control scroll lock, and there we go. We've got the manually initiated crash. Let's take a zoom in. It's stop code E2, and the description up here at the top is the end user manually generated the crash dump. So what I'm going to do now is go back and analyze that previously saved copy of a dump generated that way, and we're going to take a look to see if we can figure out what's going on. So open crash dump, hang, and one of the first things we're going to notice is that the analysis, if we took bang in the analyze-v, isn't going to be terribly helpful. Because we've manually initiated the crash, it just tells us, hey, the system crashed because you did it.
In fact, the driver that it blames is really the
i8042 port driver right here. It's really the keyboard driver for the PS2 keyboard, which called KBugCheckEX. So it says, hey, that's the guy that caused it ultimately. And the stack trace is what we want to look at. And the stack trace shows us that MyFault was executing, the MyFault driver, and was interrupted by the keystroke that we typed in, the control, scroll lock. The i8042 port driver saw that sequence and then called its own internal process crash dump function, which called KBugCheckEX. So here, our analysis would focus on myfault.sys being on the stack at the time of the crash on the processor that crashed the machine. Let's take a look at that driver. Maybe it's got an infinite loop bug in it that was causing the machine to crash, and that's exactly what type of bug the MyFault driver exhibited to hang the machine in this case. I've actually got a real-world example, Dave, from one of my home systems that was periodically hanging, and I configured it to do crash on control scroll lock to get a crash dump of it, and let's go take a look at that. And that was a single processor hyper-threaded system, so we're going to have to look at both processors in that case. So again, manually initiated crash dump code, there E2, which we saw just a moment ago. And let me do a bang thread to look at the state of the stack. And what we see here on the stack, if we read from the bottom up, is a particular driver, WPN 1111. We see it multiple times on the stack, and then we see it call into Windows networking driver, NDIS acquire spinlock, which called in the HAL. A spinlock is a synchronization resource, and when you see a hang, it's probably caused because of some synchronization resource problem or the infinite loop that we just saw. So this is a different example. If we look at the prompt down here, we see that the kernel debugger is focused on CPU 0 of this multiprocessor system. So I'm going to switch the focus to the other processor by saying tilde1 and typing bang thread again on that processor. And the stack looks really similar to what we just saw with that WPN 111 driver calling into NDIS acquire spinlock. This looks like a classic example of the driver having a synchronization problem where one processor has the lock, the other processor tries to grab the lock, and the system ends up freezing. Now what is this WPN 1111 driver? Let's see if LMKM, which is a match on that string, tells us anything. Whoops, I forgot the V, LMKV. And unfortunately, this is a situation where the version information associated with that driver isn't currently in the physical memory of the system. But because this was my own home system, I was able to go to this driver image right here, look at the version information, see what version I had, go to the vendor's website, see that they had a more recent version of this driver, and download the updated driver. The hang problem went away.
I bet that was really satisfying for you, Mark.
It was. Yep.
So the last scenario for dealing with systems that are crashing or hanging with no crash dump is a little bit different, and it's a case where the system is not fully hung. It's still responsive enough to run some troubleshooting tools, but you know something's not operating properly. Maybe applications are hanging, client applications on a server are hung. So you want to look at the state of that system without having to crash it, because the technique we suggested for a hung system is to break in with a kernel debugger, which stops the operation, or manually initiate a crash from the keyboard. If this is a production system, perhaps it's not sick enough that you need to reboot it, but you would like to take its kernel state offline to send to somebody to analyze. Well, a tool that Mark wrote for our third edition of our book, Inside Windows 2000, called LiveKD, which is now available as a free download from sysinternals, tricks the standard Microsoft kernel debuggers into thinking they're looking at a crash dump, when in fact they're being directed to examine the live memory of the currently running system. LiveKD allows you to perform what is now available in Windows XP as local kernel debugging on Windows 2000 and NT4. But one of the debugger commands that happens to work when you use LiveKD to run the Microsoft debugger is the .dump command. That's the command we talked about earlier that you can use to save the state of the system's memory from a system you've broken into onto the host debugger machine. Well, using LiveKD, you can run the standard Microsoft debugger and use .dump to basically make a memory dump of your system while it's up. And then what can you do with that dump? Send it to Microsoft for further analysis.
In fact, it's Microsoft that even told us about this technique. We didn't think of it ourselves. I had independently 2 PSS engineers that are responsible for analyzing customer systems that are acting unreliably say that they've used this to capture images of the customer systems that they could then send into Microsoft for analysis.
So for more information on digging deeper into analyzing crash dumps and some of the options in the debugger tools, first of all, our book Windows Internals has a chapter dedicated to crash dump analysis. Also, the Debugging Tools help file that we've opened several times does have some sections with more advanced analysis techniques, like manually walking a stack and some other common debug scenarios that would be worth walking through in your own time. And finally, the Microsoft Knowledge Base has a number of advanced debugging articles that you might want to examine.
We thought we'd conclude on a little bit of a lighter note. We've spent a lot of time talking about crashes and hangs, something that's probably painful for you if you're watching it. The only reason you're watching is because you've got those kinds of situations in your network. So let's lighten things by taking a look at some real-world crashes out in the public. And you might have seen these at your airport or at a bank or at a phone kiosk. We've got some examples we've been collecting over time that are kind of interesting and amusing at the same time. Here's an example of a blue screen at an airport luggage claim on the monitor. So it seems like airports are one of the places where I've seen blue screens more than other places. This one's at a train station in Barcelona. One of the ticket vending machines has blue screened, you can see here, and it appears that somebody's gotten really angry at this and just slapped stickers all over the machine.
This one actually was after speaking at a conference in Zurich. This is a baggage claim in the Zurich airport. What I was impressed with when I looked more closely at the screen, the text for the blue screen is actually translated into German. And that really shows Microsoft's commitment to the international market to translate even the blue screen text into the localized language.
This next one is, again, another airport one. Like we said, it's common. Here over on the right side, this right monitor is crashed, and a little bit of Christmas cheer, I guess, for the passengers arriving to check in. This one I find it kind of interesting because you wouldn't think that a machine that crashes all the time would be one of CompUSA's best-selling computers. And this one is Dave. This is you a couple years ago. You were going on vacation with your family, if I remember correctly. You were at the Continental check-in counter at LaGuardia, and your wife took this picture of you. You've got that smug smirk on your face because you've looked at the screen, figured out the cause of the crash, and have turned to the people in line behind you and explaining the reason for the crash.
They didn't seem very interested. This is the former Iraqi information minister. He now works for Microsoft Public Relations. There are no bugs in our software, never I tell you, he says.
And this one is one of the largest blue screens that have probably ever taken place. It's on one of the largest hotels in the world. If we zoom back a little bit, you'll see over here part of the logo. This is the MGM Grand Hotel and Casino in Las Vegas. And this one, probably the most public blue screen ever. This is right in the middle of Times Square. You can see it's probably dusk around rush hour. Microsoft's probably not very pleased to see that one.
This one makes me a little worried to ride the subway. This was on a sign outside one of the subway stations. I think it was near Times Square. And if you look very closely, you can see it was a page fault in non-paged area. So I really wanted to go find the console and enable verifier and try to reboot and get a better crash.
Or at least flip the screen on its side so that it would show more text, and you could maybe get some idea from that. And this final one is telephone in UK, British Telecom internet kiosk that is blue screened.
So although we've seen a number of these public blue screens, I think it is certainly the exception. Windows reliability is at a point that it's never been at before. It's unusual to see them, but it is kind of amusing to see them in some of these public places.
And many of these blue screens are actually older versions of Windows on top of that.
Yeah, NT4 and earlier. Now, if you really like to see blue screens, you could actually wear one on your shirt. There is a website, which I'm going to go to now, that provides blue screen t-shirts. It's www.errorwear.com. That's errorwear.com. They have a variety of software crash t-shirts, Windows 95 and Windows NT and Windows 2000. So if we go to PC errors, scroll down, there's the 95 blue screen of death, the female version. And then here we have the NT4 and Windows 2000 blue screen of death t-shirts.
Oh, look at that, Dave.
And even our name is mentioned there. I think it says, this extremely hardcore shirt was made with the help from David Solomon and Mark Rasimovich. I got my name first.
In fact, you had nothing to do with generating that image for that, so that's a little annoying. It's also kind of annoying that they put our names there, but we don't get any kind of commission off the sales.
Now, you know what's nice, though? There is no XP blue screen of death shirt.
We just, on principle, refused to provide them.
XP is so reliable that that would be a shame to wear. Now, what was funny is the day that we actually wore these shirts at Microsoft. Mark and I wore, I think, NT4, and you wore Windows 2000 into the Microsoft building where the Windows kernel engineers are. And most of them thought it was pretty funny, but one of the senior management personnel that saw us was not amused to see us wearing a blue screen.
Basically told us to get out of his office. Yeah. So we weren't making any good friends there with that shirt with him. But finally, we want to leave you with a screensaver that I wrote that you can use if you've forgotten what the blue screen looks like, you want to remember what it looks like, or you want to use it on somebody else's machine. We'll tell you about that in a second. The SysInternals Blue Screen of Death screensaver, which unfortunately our screen capture program won't let us capture for you to display. So you need to go to sysinternals.com and download it. Stick it in your Windows System 32 directory. It'll show up here in the screensaver drop-down. If you select it, it accurately simulates a blue screen specific to the version of Windows that you're running on. So if you're running on NT4, it even works all the way back then. It looks like NT4s, all the way through 64-bit Windows XP, and I haven't yet updated it for Vista. Maybe by the time you're looking at this, there will be a Vista updated version.
Maybe Vista will be so reliable that there just won't be any more.
That's right. Maybe I just won't even bother because it would just be so unrealistic. And the fake disk activity there that you see Dave has popped up in the dialog box really makes more sense on the NT4 version because NT4 used to spit out check disk information on the blue screen, and if you select that, the blue screen screensaver does that and tries to pretend or basically simulates finding a lot of problems on the disk. And it also causes the disk to grind as an added level of authenticity.
Just so I can get that easily, where can I find it on SysInternals, Mark? I'm going to go to sysinternals.com.
Yes, SysInternals, the miscellaneous section.
So I'm clicking on miscellaneous on the left, scroll down.
There it is.
Blue screen, version 3.2. So you've been working hard on that tool, I can see, Mark.
And what I'm really proud of with that screensaver is that it not only mimics the blue screen, but it also simulates a reboot, where it looks like this desktop's about to come up and then it crashes again with a different randomly chosen error code and stop code.
Now what's really nasty is to actually run this on somebody else's computer. And you've written another tool that makes that relatively straightforward, and that's psexec. So you can bring up a command prompt, use psexec to remotely run the blue screen screensaver on somebody else's machine. Of course you need admin rights. So psexec -i, -d, -c, C is copy the file over, specify the path to the screensaver, which you have on your local machine, /s, which tells the screensaver to actually execute. You would specify the remote machine name, and all of a sudden, poof, on the remote machine, a blue screen will come out. Now, this blue screen screensaver has...
it's fooled kernel developers at Microsoft. It's fooled the lead of the Windows development team or program, the lead manager.
But what was the most fun is when I fooled you with your own screensaver.
Yeah.
So Mark and I were preparing for a a class we were giving at a Microsoft conference, and it was about 11:30 at night. We had been up late, and we had just flown in. It was in a European country. We had carefully set up a demo that we were practicing, and I had put a shortcut on my start menu to the blue screen screensaver. I had called the shortcut something else. In fact, I called it, I think, Outlook 11. It was a new version of Outlook. In the middle of our preparing for this demo, I said, hey, Mark, you want to see the new version of Outlook I have installed? And Mark said, sure. So I went and clicked on the Outlook 11 shortcut. Boom, blue screen. Mark flies back in his chair in dismay and disgust because we had lost all this setup time. I was biting my tongue. The system goes through the reboot, and it blue screens again, and then Mark
realized that you were playing a joke on me. But what's funny is that you'd used this, I'd accidentally used this screensaver to fool you previous to that. At a conference we were both attending, I was presenting in a different room, and we took a break. The screensaver was running on my laptop, so it kicked in. And I go out into the hallway, and a few minutes later, Dave comes rushing down the hallway saying, Mark, you better get back to the room. Your system's crashing and rebooting spontaneously. You need to fix it before you have to resume. And I said, Dave, calm down. It's just the screensaver. So I got you too.
Now, I think there's a little warning, though, about the screensaver.
Yeah, if you're going to use it on somebody else's machine, or make sure that you've got the authority to put it on that machine. Do not, and even if you've got the authority, do not put it on a production server. Because you run it on the production server, somebody might come into the room, see it crashing, hit the reset button, and really reboot the machine. And that's exactly what happened when one user downloaded the screensaver, put it on a system at their work, and caused the machine to reboot in the middle of the day during peak production hours. And this caused the machine to actually not even reboot. It entered a non-rebootable state, not related to the screensaver, but just by chance it wouldn't reboot. So they were down for hours because of this. And the employee got fired. I got a nasty note from the manager saying, you should be ashamed of yourself. You shouldn't be publishing a tool like this. You should withdraw it. Look, I just fired somebody over it. So be careful, especially if you use the PSExec switch to run it remotely on your boss's machine, that they're not going to come back at you and get mad.